The era we are about to explore is one that shaped the course of modern history, a time of uncertainty, ambition, and global tension. The Cold War, a standoff between the United States and the Soviet Union, had captured the world in its icy grip. Nuclear arms races, political intrigue, and espionage defined international relations as both superpowers vied for supremacy on the earth and in the heavens. This period of time, stretching from the end of World War II in 1945 to the fall of the Berlin Wall in 1989, was filled with dramatic societal challenges that seemed to point toward a future either shaped by fear or by progress. The geopolitical landscape was marked by divisions. In Europe, a crumbling continent saw the rise of the Eastern Bloc under Soviet influence, while the Western world rallied under the banner of democracy and capitalism. The space race, initiated by the Soviets' launch of Sputnik 1 in 1957, ignited an unparalleled competition that would last for decades. The primary question, however, was not about the space the two nations would explore, but about the power and prestige that space exploration could bring. The year was 1961, and the world was teetering on the edge of space exploration as an extension of the Cold War conflict. The United States had already begun to feel the weight of the Soviet Union's achievements in space, with the successful launch of Yuri Gagarin into orbit in 1961, signaling the Soviet Union's technological might. At the same time, the American space program, led by NASA, found itself at the crossroads of technological limitations, political pressure, and an urgent need for a compelling response. The overarching mission, to establish dominance in space and to explore new frontiers beyond Earth's atmosphere, became not only a matter of national pride but of survival, in a world where every technological advancement was seen through the lens of military superiority. The United States, under President John F. Kennedy, took the first definitive step toward a bold vision, sending a man to the moon and returning him safely to Earth. It was an audacious goal, but one that could capture the imagination of a nation and, indeed, of the world. This mission, to put a man on the moon, was not merely about exploring the unknown or advancing science. It was about proving to the world that the United States could not only compete, but could win in the ultimate arena of human achievement. It was about overcoming not only technological barriers, but societal skepticism, political pressures, and internal doubt. The success of the mission was viewed as vital to the success of the United States on the world stage, and was essential to the broader fight for ideological supremacy in the Cold War. The significance of the mission was immense. It promised to unite humanity in a shared quest for knowledge, while simultaneously challenging the boundaries of what was possible. The stakes were higher than ever before, with the success or failure of the mission having the potential to alter the trajectory of the global order, both politically and scientifically. As key figures emerged in this space race, the roles of scientists, engineers, astronauts, and politicians became indispensable. The commitment to space exploration had turned into a national endeavor, with personalities like President Kennedy, NASA Administrator James Webb, and visionary astronauts like Alan Shepard and John Glenn playing critical roles in the unfolding drama. Behind these towering figures, a network of scientists, engineers, and workers labored tirelessly to make the impossible possible. And yet, the path to the stars was not without its difficulties. Technological limitations and a lack of understanding about the effects of space weather and solar activity on both spacecraft and astronauts posed formidable challenges. The sun, ever present in the sky but largely misunderstood, had an unseen but powerful influence on the technological systems necessary for these missions. Solar flares and the volatile nature of space weather were not yet fully understood, yet they had the potential to jeopardize the success of missions and the safety of astronauts. In the midst of these tensions, the mission to reach the moon would soon become the defining moment in history, not only for the United States but for the entire world. The conquest of space was not simply about moving beyond the Earth. It was about understanding the very forces that govern the universe. It was about learning how to predict and protect against the very elements of space weather that could threaten these bold endeavors. With the stage set, the world would soon witness a revolution in space exploration, one that would lay the groundwork for future missions and ultimately shape humanity's destiny in the cosmos. The journey that would begin in the next chapter was more than a leap for mankind. It was a defining moment in the human spirit's quest for discovery and understanding. The early days of space exploration were filled with promise, but the road to success was fraught with challenges. In the 1960s, as the United States and the Soviet Union continued their race to space, both nations found themselves confronting an array of obstacles: technical, political, and social. Despite the initial optimism, the reality of the difficulties ahead soon became apparent. Technologically, the United States faced a series of setbacks. Rocketry, spacecraft design, and even the most basic understanding of space conditions had yet to evolve to the point where a successful manned mission to the moon was achievable. The immense distances, the cold void of space, and the dangers posed by radiation from the sun were all factors that the scientists and engineers at NASA had to contend with. In many respects, the world was flying blind, relying on an untested combination of experimental technology and theoretical physics to move forward. Even the most experienced scientists struggled to predict how human bodies would react to the stresses of space travel. There were concerns about weightlessness, radiation exposure, and how spacecraft would be able to protect astronauts from the immense temperatures and vacuum of space. Yet it was not only the technical barriers that posed a challenge. It was also the intense pressure from the global community, the American public, and most crucially, the political leadership of the time. The Cold War had defined the era, and space exploration was increasingly seen as a political battleground. President John F. Kennedy's decision to pursue a manned mission to the moon, outlined in his famous 1961 speech, was one of both vision and necessity. Kennedy understood that the space race was not simply about scientific achievement, but was also about showing strength in a time of global tension. For him, the United States could not afford to fall behind in the race for space dominance. As he famously declared, the U.S. would go to the moon, not because it was easy, but because it was hard. This vision, bold and ambitious, gave birth to the Apollo program. The mission was clear: to land a man on the moon and return him safely to Earth. But the vision was not just about the destination. It was about proving the ability of the United States to push the boundaries of human knowledge and capability. In Kennedy's words, it was about taking a giant leap for mankind, not just for the United States. But the road to that leap would require overcoming a series of hurdles that no one could have fully anticipated. At the heart of these early challenges was skepticism. The idea of sending a human to the moon seemed like a far-off dream to many. Critics argued that the resources could be better spent solving problems on Earth, from poverty to civil rights. There were also those who doubted the feasibility of such a mission. Questions about the technical ability to build spacecraft capable of surviving the journey, the capability to navigate the complexities of lunar landing, and the very real concern of what might go wrong. Despite the doubts, there was a growing consensus within the government and across the scientific community that the space race was a crucial step in the advancement of both technology and national security. The United States was determined to secure its place in space history, and Kennedy's vision gave NASA the political backing it needed to push forward, despite the obstacles that lay ahead. Beyond the technological and political challenges, the broader society was also feeling the tension. The Cold War loomed large over every decision, and space missions were viewed as an extension of military might. Yet, space exploration was also a beacon of hope and curiosity for the American public, who eagerly followed every launch, every news bulletin, every piece of information that came from NASA. The space race became a symbol of American ingenuity and determination. In the early years, before the successful landing of Apollo 11, the American space program faced a series of trials that seemed insurmountable. The first manned spaceflights had been untested, and each failure or setback was met with both despair and resolve. But for every failure, there was a lesson learned, and with each lesson, NASA inched closer to its goal. The vision of reaching the moon and doing so first was not just about technological innovation. It was about uniting the country behind a common purpose. As the United States faced the challenges of the Cold War, the promise of space exploration offered a way to channel national energies into something that transcended earthly conflicts. It was about pushing the boundaries of human experience and standing on the precipice of something entirely new, a new frontier not of land, but of the stars. The groundwork had been laid. The obstacles would not vanish overnight, but the vision was now firmly established. The journey would continue to test the limits of human perseverance, technology, and collaboration. The road ahead was uncertain, but with visionary leadership, scientific rigor, and a commitment to overcoming every challenge, humanity was about to take its first steps toward the moon. Behind the vast machinery of the space race were individuals, scientists, engineers, astronauts, and political leaders, whose courage, intellect, and perseverance would ultimately define the mission to the moon. These were the people who had the vision to see beyond the stars and the will to make the impossible possible. Their stories are intertwined with the grand narrative of space exploration, and without them, the extraordinary achievements of the Apollo program might never have come to fruition. At the forefront of these efforts was President John F. Kennedy, whose bold vision for space exploration galvanized the nation. Kennedy's declaration that the United States would land a man on the moon by the end of the decade was a defining moment. His words inspired not only the nation but the world, setting a goal that seemed almost unattainable. Kennedy's leadership was crucial in securing the necessary funding, political support, and national attention to ensure that NASA's Apollo program would succeed. His vision turned a seemingly far-off dream into a tangible goal. Alongside Kennedy, there were a handful of individuals whose efforts were pivotal in bringing the dream of space exploration into reality. One such figure was Wernher von Braun, a German-American rocket scientist who played a critical role in the development of the Saturn V rocket, the powerhouse that would carry astronauts to the moon. Von Braun's expertise and his ability to lead a team of engineers and scientists were indispensable in overcoming the technical hurdles of building a rocket powerful enough to reach the moon. His past as a member of the German rocket program during World War II had been controversial, but his talents could not be denied. Von Braun's work on the Saturn V rocket remains one of the most significant contributions to space exploration. Then there was James E. Webb, NASA's administrator from 1961 to 1968, who played a pivotal role in overseeing the Apollo program. Webb's leadership was instrumental in securing the resources necessary for the program's success. He had a calm, diplomatic demeanor and was known for his ability to navigate the complex political landscape of the time. Webb was a key figure in coordinating NASA's operations, from the technological development to the management of the various contractors and engineers working on the mission. Under his guidance, NASA transformed from a relatively small space agency into a powerhouse of scientific achievement. On the ground, the engineers and scientists who worked tirelessly to develop the spacecraft and technologies that would be used in the Apollo missions were just as important as the astronauts themselves. These individuals, many of whom worked behind the scenes, developed the systems that made the moon landings possible. They were the unsung heroes whose innovations in navigation, communication, life support, and propulsion technology enabled the crew to survive and succeed in the harsh environment of space. Among these engineers was Margaret Hamilton, who served as the director of the Software Engineering Division at MIT Instrumentation Laboratory. She and her team developed the software that ran the Apollo spacecraft's guidance and navigation systems. Hamilton's contributions were groundbreaking. Her work on the software that powered the lunar modules helped ensure the success of Apollo 11. Her leadership in the creation of complex, fault-tolerant systems demonstrated the importance of software development in space missions, a field that was still in its infancy at the time. Meanwhile, the astronauts themselves became the face of the Apollo missions. Neil Armstrong, Buzz Aldrin, and Michael Collins were the crew of Apollo 11, the first mission to land humans on the moon. Neil Armstrong, a former Navy pilot and test astronaut, was chosen as the mission commander. He was known for his calm demeanor under pressure and his ability to think critically in the most stressful situations. His famous words upon stepping onto the lunar surface, "That's one small step for man, one giant leap for mankind," encapsulated the significance of the moment, not just for the United States but for all of humanity. Buzz Aldrin, the lunar module pilot, was another key figure, and FASIC. Aldrin was an astronaut with a passion for space exploration that was unmatched. His extensive training and his role as the second man to walk on the moon placed him in the history books. But his contributions extended far beyond the lunar surface. Aldrin was instrumental in the development of spacewalks and extravehicular activities, EVAs, and he would later work to promote future space exploration missions. Michael Collins, the command module pilot, remained in orbit around the moon while Armstrong and Aldrin made history on the lunar surface. Though Collins did not have the same public exposure as Armstrong and Aldrin, his role was no less important. He piloted the command module alone, ensuring that the spacecraft remained on track for the rendezvous and that the crew's return to Earth was executed flawlessly. Collins' contribution to the success of the mission was vital, and his solitude in orbit was a testament to the courage required to undertake such a dangerous mission. The teamwork between the astronauts, engineers, scientists, and political leaders was what made the Apollo program a success. Collaboration across NASA's centers, with various teams working on different aspects of the mission, ensured that each component of the spacecraft was tested and refined before launch. Engineers worked around the clock to solve problems with the spacecraft's life support systems, propulsion, and communications equipment. Scientists contributed their expertise in understanding the moon's surface, the effects of space weather, and the risks posed by radiation in space. Together, they overcame the enormous challenges that stood in the way of the mission. These key figures, with their individual expertise and collective determination, helped transform what was once considered impossible into a reality. Their collaboration and commitment to the mission demonstrated the power of human ingenuity and teamwork. They faced not only technological barriers, but also personal and professional challenges. Yet, in the face of adversity, they remained focused on the singular goal of reaching the moon. In the coming chapters, we will explore how these figures, alongside the countless others who contributed to the Apollo program, played crucial roles in overcoming the technological, social, and political obstacles that lay ahead. The story of their work and dedication forms the backbone of one of the greatest achievements in human history. The mission to the moon was not only about human courage and ambition, it was also a triumph of technology and engineering. Every step of the journey required advancements in scientific knowledge, precision, and the development of technologies that had never before been attempted. The technological breakthroughs that made the Apollo missions possible were numerous and groundbreaking, pushing the boundaries of what was thought to be achievable. From the development of rockets capable of leaving Earth's atmosphere to the creation of the sophisticated spacecraft that would land on the moon and return safely to Earth, each innovation was a vital step forward in the quest to explore the cosmos. The first and most significant technological challenge that faced the United States in its race to the moon was the development of a rocket powerful enough to escape Earth's gravity. The solution came in the form of the Saturn V rocket, designed by Wernher von Braun and his team at NASA's Marshall Space Flight Center. The Saturn V was a marvel of engineering, towering at 363 feet, 111 meters, and capable of delivering over 7.5 million pounds of thrust, enough to send astronauts on a journey to the moon. The rocket was a multi-stage behemoth, designed to break through Earth's atmosphere and accelerate the spacecraft on its trajectory toward the moon. The first stage, powered by 5 F-1 engines, provided the initial lift, burning fuel at an unprecedented rate to propel the rocket into space. Once the first stage burned out, the second and third stages kicked in, further accelerating the spacecraft to the necessary speed to reach lunar orbit. The Saturn V was a technological marvel, not only for its sheer size, but for its reliability. It became the backbone of the Apollo program, with a total of 13 successful launches, including the iconic Apollo 11 mission. But the Saturn V rocket was just the beginning. Once the spacecraft reached space, it had to safely transport the astronauts to the moon, land them on its surface, and return them to Earth. This required the development of a sophisticated spacecraft capable of surviving the harsh conditions of space while ensuring the safety of the crew. This was where the Apollo Command/Service Module, CSM, and Lunar Module, LM, came into play. The Command/Service Module, designed by North American Aviation, was the primary spacecraft that housed the astronauts for most of the mission. It was equipped with the necessary life support systems, navigation tools, and propulsion capabilities needed to get the astronauts to and from the moon. The spacecraft's heat shield was a crucial component in ensuring that the crew could safely re-enter Earth's atmosphere after their mission. The service module, which provided power and other vital systems, was jettisoned just before re-entry, allowing the command module to return safely. The lunar module, on the other hand, was a highly specialized spacecraft designed to land on the moon and return the astronauts to the command/service module orbiting above. The LM was a complex, fragile, and ingenious design, with legs capable of landing on the moon's uneven surface, and engines that allowed it to lift off again after the mission was complete. The lunar module had to operate in the vacuum of space, without the protection of Earth's atmosphere, and it had to function in a completely new environment. The technology used to ensure that the module could operate on the moon's surface was groundbreaking, involving a combination of lightweight materials, advanced navigation systems, and new methods for ensuring the astronauts' safety during lunar landings. Another key technological breakthrough was the development of the Apollo Guidance and Navigation System, a system that allowed the astronauts to navigate through space with unprecedented precision. The guidance system, developed by MIT's Instrumentation Laboratory under the leadership of Margaret Hamilton, was responsible for guiding the spacecraft throughout the mission, from launch to lunar landing. It calculated the spacecraft's position and velocity, and provided real-time data to the astronauts on their trajectory. The system was programmed to take over in critical moments, such as the descent to the lunar surface, when human control was limited by the complexity and precision required. One of the most critical breakthroughs was the development of the life support systems that ensured the astronauts' survival in space. These systems, which were tested rigorously throughout the early years of the Apollo program, regulated the spacecraft's temperature, air pressure, and oxygen levels. They also removed carbon dioxide from the air to prevent poisoning and ensured that the astronauts had a steady supply of food and water. These systems were essential for the astronauts' survival during the long-duration mission and had to be both reliable and robust, capable of operating in the harsh and unpredictable environment of space. Communication systems were another area of technological development. The Apollo missions required a communication network capable of maintaining contact between the astronauts and Earth at all times. This was achieved through the development of a global network of ground stations, known as the Spacecraft Tracking and Data Acquisition Network, STADAN, which ensured that Apollo spacecraft could be monitored anywhere in the world. The communication technology used for these missions was state-of-the-art, allowing real-time voice communication between the crew and mission control, as well as the transmission of telemetry data, images, and scientific experiments back to Earth. Equally important were the technological advances in understanding the moon's environment and how to protect astronauts from the dangers posed by space weather and radiation. One of the most significant hazards faced by the Apollo missions was the solar radiation and the unpredictable nature of solar flares. NASA had to develop methods for predicting and shielding against solar activity that could potentially endanger the astronauts. Understanding space weather and solar radiation was a challenge in its own right, and the lessons learned in the Apollo program would form the foundation for future space exploration. Perhaps the most visible technological breakthrough was the development of the spacesuit. The Apollo spacesuit, developed by NASA and made by ILC Dover, was a highly specialized garment designed to protect astronauts during lunar EVA, extravehicular activity. The suit was made of multiple layers of fabric and insulation, with a life support system that supplied oxygen and removed carbon dioxide. It was designed to withstand extreme temperatures and protect the astronaut from the vacuum of space. The helmet featured a gold-coated visor to shield the astronaut from the sun's intense radiation, and the suit included a portable life support system, PLSS, that allowed astronauts to move freely on the moon's surface for extended periods. These technological breakthroughs, along with the dedication and hard work of the thousands of engineers, scientists, and astronauts involved, were the foundation upon which the success of the Apollo program was built. The innovations developed during this time revolutionized space exploration and laid the groundwork for the missions that would follow. From the Saturn V rocket to the spacesuits worn by astronauts, each technological achievement was a testament to human ingenuity and perseverance, proving that with the right combination of vision, effort, and determination, humanity could achieve the seemingly impossible. The story of the Apollo program is a series of defining moments, filled with triumphs, challenges, and monumental achievements. These missions, each one building on the last, would eventually culminate in one of the greatest accomplishments in human history, landing a man on the moon. The path to that historic moment was not smooth, but it was a journey marked by perseverance, ingenuity, and the willingness to confront both technical and emotional obstacles. First major event in this story was the successful flight of Apollo 11. the mission that would ultimately bring Neil Armstrong, Buzz Aldrin, and Michael Collins to the moon. The mission, launched on July 16, 1969, was the culmination of years of planning, development, and testing. The Saturn V rocket, having undergone numerous tests, was ready to lift the astronauts off the ground. For the first time, a manned mission would leave Earth's atmosphere with the goal of reaching the lunar surface. As Apollo 11 made its way to the moon, the world held its breath. The spacecraft, composed of the command/service module and the lunar module, was now on a trajectory that would take it 240,000 miles from Earth. For the astronauts, the journey was a time of reflection, training, and preparation. As they hurtled through space, they were aware of the enormity of the task ahead of them. The moon was no longer just a distant celestial body, it was now within their reach. When Apollo 11 arrived in lunar orbit, the team began its final approach for landing. The lunar module, separated from the command module, descended toward the moon's surface. However, as the descent began, problems arose. The landing site was littered with large boulders, and the lunar module's guidance system indicated that it was headed for a rocky, hazardous area. Armstrong took manual control of the spacecraft, guiding it away from the dangerous terrain. In a moment of intense concentration, Armstrong's calm leadership and expertise shone through. With just seconds of fuel remaining, the lunar module finally touched down safely on the moon's surface. Armstrong's words as he stepped onto the lunar soil, "That's one small step for man, one giant leap for mankind," became etched in history, forever defining the achievement. The significance of Apollo 11 cannot be overstated. It marked humanity's first successful landing on another celestial body. For the astronauts, the experience was overwhelming. Buzz Aldrin joined Armstrong on the surface, and together they spent over 2 hours exploring the moon, collecting samples, and planting the American flag. Color flags. The visual of them walking on the barren, dusty surface of the moon, with Earth visible in the blackness of space, would be forever seared into the collective memory of humanity. The mission's success demonstrated not only the power of American ingenuity, but also the potential of space exploration to unite humanity in the pursuit of knowledge. But while Apollo 11's success was a triumph, it was not without its challenges. The mission was not without its failures, and the risks involved were substantial. The astronauts encountered numerous technical difficulties, and there were constant concerns about the dangers of radiation, micrometeorite impacts, and the reliability of the spacecraft. These risks would be encountered again in future missions, highlighting the unpredictable nature of space exploration. Apollo 12 followed soon after, with the goal of landing in a different area of the moon, known as the Ocean of Storms. This mission, launched in November 1969, would prove to be one of the most challenging. Shortly after launch, Apollo 12 was struck by lightning twice, causing significant damage to the spacecraft's electrical systems. The team, led by Commander Charles Pete Conrad, was forced to work through a series of difficulties, including a failure in the spacecraft's guidance system. Despite these issues, Apollo 12 successfully landed on the moon, making it the second successful lunar landing in just a few months. Conrad and his fellow astronaut Alan Bean spent over 7 hours on the lunar surface, collecting samples and taking photographs. The success of Apollo 12 was another testament to the astronauts' ability to adapt and overcome adversity in the face of potentially catastrophic situations. Apollo 13, however, would be the mission that tested the limits of human ingenuity and courage. Launched in April 1970, Apollo 13 was supposed to be another routine lunar landing mission. But midway through the journey, disaster struck. An oxygen tank exploded in the service module, crippling the spacecraft's power systems and leaving the crew stranded in space, 200,000 miles from Earth. The mission, led by Commander Jim Lovell, was in grave danger. The explosion had caused a loss of life support systems, and the spacecraft was rapidly losing oxygen. It became clear that the Apollo 13 crew would not be able to land on the moon. The primary objective shifted from exploration to survival and a safe return to Earth. What followed was a race against time. NASA's engineers and the Apollo 13 crew had to work together to solve the life-threatening problems caused by the explosion. The astronauts were forced to improvise, using limited supplies and relying on the ingenuity of the engineers on the ground. The iconic "Houston, we have a problem" moment was only the beginning of the team's relentless efforts to restore power, conserve oxygen, and navigate the spacecraft back to Earth. Through teamwork, determination, and incredible problem-solving, Apollo 13's crew made it home safely. While the mission had not achieved its original goal, it became a triumph of human resilience, highlighting the power of collaboration and the will to overcome seemingly insurmountable odds. Apollo 14 followed in 1971 with Commander Alan Shepard, the first American in space, returning to the Moon. This mission marked a return to lunar exploration after the near disaster of Apollo 13. Shepard and lunar module pilot Edgar Mitchell spent more than 30 hours on the lunar surface, conducting experiments and collecting samples. This mission was also notable for Shepard's famous golf shots, where he hit 2 golf balls on the Moon, showcasing the human need for lighthearted moments even in the face of great challenges. In 1972, Apollo 17 marked the final mission of NASA's Apollo program. This mission, commanded by Eugene Cernan, marked the last time humans would set foot on the Moon for more than 50 years. Apollo 17's crew spent over 3 days on the lunar surface, conducting experiments and collecting rock samples, including the famous orange soil sample. The mission's success solidified the United States' dominance in space exploration and was the final chapter in the Apollo program. The end of Apollo 17 marked the closing of an extraordinary era in space exploration and set the stage for the future of human spaceflight. The missions that followed Apollo 11 were full of extraordinary moments, each contributing to the growing body of knowledge about the Moon, space travel, and human adaptability in space. These missions, from the triumph of Apollo 12 to the harrowing drama of Apollo 13, and the final achievements of Apollo 14 and Apollo 17, all contributed to the ongoing legacy of space exploration. Each mission was a step closer to understanding the mysteries of space and the capabilities of human ingenuity. These events and missions were not just milestones for the United States, but for humanity as a whole, marking the first steps toward a future where space would no longer be a realm reserved for dreams but a new frontier to be explored. No mission in the history of space exploration has been without its moments of crisis. But the true measure of success lies not in avoiding these crises but in overcoming them. One of the most significant crises to unfold during the Apollo program was the Apollo 13 mission, which, despite its initial failure, ultimately became a shining example of resilience, ingenuity, and teamwork. The crisis was not just a technical setback, but a life-threatening emergency that required the best minds in space exploration to work together under intense pressure to bring the astronauts safely home. On April 11, 1970, Apollo 13 launched from Kennedy Space Center, bound for the Moon. The mission was supposed to be routine, another step forward in the series of lunar explorations. However, just 56 hours into the flight, disaster struck. A routine stir of the oxygen tanks in the service module caused an explosion that ruptured one of the oxygen tanks, sending the spacecraft into a state of immediate peril. The crew commander Jim Lovell, lunar module pilot Fred Hayes, and command module pilot Jack Swigert were faced with a crisis that no one could have anticipated. The explosion caused the loss of the spacecraft's primary source of oxygen and power, leaving the astronauts stranded in space, far from Earth, with limited supplies of food, water, and oxygen. The most immediate concern was the life support systems. Without functioning oxygen, the crew would not survive. NASA's Mission Control, led by Flight Director Gene Kranz, immediately sprang into action, realizing that the most important objective had shifted from reaching the Moon to ensuring the safe return of the astronauts. The first response was a cold, calculated assessment of the spacecraft situation. The crew had to shut down most of the spacecraft systems to conserve what little power remained. Every decision was weighed carefully, as there was no room for error. As the spacecraft continued its journey into deep space, it became clear that the original mission plan was no longer viable. The astronauts, who had been trained for the journey to the Moon, now had to adapt to an entirely new mission, returning home with a damaged spacecraft and dwindling resources. In the face of this crisis, the efforts of NASA's engineers, technicians, and flight controllers were nothing short of heroic. They had to devise a plan to get the astronauts back to Earth safely, One of the key challenges was finding a way to use the lunar module intended for landing on the moon as a lifeboat. The lunar module had a separate set of life support systems that could keep the astronauts alive, but it was never meant to be used for such an extended mission, especially without its primary purpose of landing on the moon. The crew worked in close collaboration with NASA's ground team, following detailed instructions and improvising solutions to the many problems that arose. One of the most critical moments occurred when the crew had to manually figure out how to reconfigure the spacecraft's carbon dioxide scrubbers. The lunar module was not equipped to handle the increased amount of carbon dioxide produced by the astronauts' breathing over an extended period. Engineers on the ground quickly devised a way to adapt the square carbon dioxide scrubber cartridges from the command module to fit into the round holes of the lunar module's life support system. It was a moment that demonstrated the ingenuity and quick thinking that would become the hallmark of the mission's recovery. Meanwhile, the astronauts were forced to take extreme measures to keep themselves alive. They had to endure cramped conditions, with the temperature dropping and the lack of food and water making their journey even more uncomfortable. But throughout it all, they maintained a sense of calm and focus, relying on their training and trust in each other to get through the ordeal. As the spacecraft made its way back toward Earth, the team on the ground continued to monitor the situation, constantly adjusting their calculations and making corrections to ensure a safe re-entry. Despite all the odds, the astronauts were able to successfully perform a critical engine burn that would bring the spacecraft on course for a splashdown in the Pacific Ocean. On April 17, 1970, after a harrowing journey, Apollo 13 splashed down safely in the ocean, and the crew was recovered by the USS Iwo Jima. The mission, despite its initial failure to land on the moon, was considered a remarkable success in the annals of space history. The crisis had tested the limits of human resilience, and the recovery efforts had proven that, even in the face of seemingly insurmountable challenges, it was possible to overcome adversity with resourcefulness, determination, and teamwork. The impact of Apollo 13 was profound. Not only did it demonstrate the resilience of the astronauts, but it also highlighted the strength of the NASA team on the ground. The crisis had revealed the importance of rigorous training, adaptability, and the ability to stay calm under pressure. The lessons learned from the Apollo 13 crisis influenced future missions, particularly in terms of spacecraft design, safety protocols, and contingency planning. The Apollo 13 incident also had a lasting effect on the astronauts themselves. Jim Lovell, Fred Hayes, and Jack Swigert, the mission had been a life-altering experience. Lovell, who had been on the verge of making history by landing on the moon, now found himself in the position of surviving a near-fatal disaster. The ordeal bonded the crew, and they became a symbol of the human spirit's ability to endure under extreme circumstances. While the crisis of Apollo 13 was perhaps the most dramatic and public example, it was far from the only challenge faced by the Apollo program. Every mission had its own set of obstacles, technical, emotional, and physical, that had to be overcome. Apollo 11, for example, faced its own crises during the lunar landing, when Neil Armstrong had to manually take control of the lunar module to avoid a crash landing. Apollo 12 faced difficulties with its electrical systems during launch, yet managed to land successfully. Each of these moments required swift, decisive action and highlighted the importance of training, teamwork, and a deep commitment to the mission. The Apollo program was not just about achieving a specific goal, it was about learning how to handle crisis and uncertainty. The astronauts, engineers, and mission controllers involved in the program faced challenges that tested their limits and their resolve. But in the end, it was their ability to adapt, to work together, and to solve problems in real time that allowed them to overcome these crises and succeed in their mission to explore the moon. The recovery of Apollo 13, in particular, became a defining moment in the history of space exploration. It proved that failure was not the end. It was simply another opportunity to learn, adapt, and push forward. The lessons learned from the crisis would shape the future of space exploration and set a precedent for how humanity would approach the vast, unpredictable challenges of venturing into the unknown. After years of preparation, testing, and overcoming obstacles, the Apollo program was nearing its most critical and eagerly awaited moment, landing a man on the moon. The culmination of decades of scientific and technological advancements, political will, and human determination, Apollo 11 would forever mark humanity's leap beyond the confines of Earth's gravity and into the vast expanse of space. July 20th, 1969, was a day that the world would never forget. As millions of people tuned in to their televisions, the quiet hum of mission control in Houston masked the incredible pressure and tension building in the control rooms. It was the final stages of the mission, and the Apollo 11 crew, composed of Commander Neil Armstrong, Lunar Module pilot Buzz Aldrin, and Command Module pilot Michael Collins, was preparing for their descent to the moon's surface. For Armstrong and Aldrin, this would be the first human landing on the lunar surface, while Collins remained in lunar orbit, ensuring their safe return to the command module once the mission was complete. The descent to the moon was a critical phase, and it was anything but routine. As the lunar module began its descent, Armstrong and Aldrin were faced with unexpected obstacles. The landing site, initially chosen for its relative safety, proved to be filled with large boulders, which made it a far more dangerous location for landing than had been anticipated. Armstrong, in a moment of calm and decisive action, took manual control of the lunar module, carefully guiding it away from the perilous rocky terrain. Every moment of that descent required precision and skill, with Armstrong piloting the module in a series of nerve-wracking adjustments to avoid disaster. As the lunar surface loomed closer, the tension in mission control reached its peak. With just seconds of fuel remaining, Armstrong's hands remained steady, and with a final, calculated move, he brought the lunar module down on the surface of the moon, an act that would forever change history. The voice of Neil Armstrong echoed through mission control. "Houston, Tranquility Base here. The Eagle has landed." The words sent waves of relief and joy through the control rooms, but Armstrong and Aldrin were not yet done. They still had to complete the most important part of the mission, setting foot on the lunar surface. The world watched in awe as Armstrong opened the hatch of the lunar module and descended the ladder to the surface. As his boots made contact with the dusty ground, Armstrong's famous words filled the silence of space. "That's one small step for man, one giant leap for mankind." The weight of these words, and the historic moment they symbolized, was not lost on anyone watching, either on Earth or in the cramped lunar module. Armstrong's step was not just for himself, nor for the United States, but for all of humanity. It was the moment when the human race proved that its dreams of space exploration were no longer just dreams. They were becoming a reality. As Aldrin followed Armstrong onto the lunar surface, the two astronauts took their first steps together on the moon, planting the American flag and conducting experiments. The moon, a barren, desolate world just a few days ago, had become a place where human footsteps had left their mark. For over 2 hours, Armstrong and Aldrin conducted scientific experiments, deployed equipment, and collected soil and rock samples. Their movements, slow and methodical in the low gravity, were part of a choreographed sequence, each action essential to the success of the mission. The significance of Apollo 11's landing went beyond the success of the mission itself. It was a turning point in history, a moment that united people around the world in awe and wonder. The achievement spoke to humanity's shared potential for greatness, its ability to overcome the vast challenges of space, and to push the boundaries of what was possible. The moon landing was a demonstration of human ingenuity, courage, and determination, but it was also a symbol of the peaceful pursuit of knowledge. Despite the tensions of the Cold War and the fierce rivalry between the United States and the Soviet Union, the landing was a shared moment of awe for all of humanity. Back on Earth, the reaction to the landing was nothing short of ecstatic. People across the globe celebrated, and governments from all over the world expressed their congratulations. The event transcended national boundaries, creating a sense of unity in a divided world. For the United States, the moon landing was an unprecedented achievement, not just in space exploration but also in the cultural and political landscape of the Cold War. It was proof that, when unified in purpose, humanity could achieve the unimaginable. The success of Apollo 11 was also a powerful affirmation of the American space program, then. The years of hard work, the challenges faced, the doubts and skepticism, all of it had been worth it. The United States had not only won the race to the moon, but had also paved the way for future exploration. The Apollo program would continue, and the lessons learned from the success of Apollo 11 would form the foundation for the missions that followed. As Armstrong and Aldrin completed their work on the moon, realization of their achievement began to settle in. The moon landing was a culmination, but it was not the end. The success of Apollo 11 opened the door to further exploration and discovery, both on the moon and beyond. The next step was Mars, and the exploration of the outer planets. The journey that Apollo 11 had begun would extend far into the future, as humanity's desire to explore the stars would grow even stronger. When Armstrong and Aldrin finally returned to the lunar module, they left the moon with a sense of accomplishment, but they also knew that their mission was far from complete. They still had to return to the command module, rendezvous with Collins, and make the journey back to Earth. The homeward journey, while less fraught with drama, was still a critical part of the mission, as every step taken after the landing was part of a carefully orchestrated plan to ensure the safety of the astronauts. On July 24, 1969, Apollo 11 splashed down in the Pacific Ocean, and the crew was picked up by the USS Hornet. The world's eyes were fixed on the recovery, and the safe return of the astronauts marked the successful conclusion of the first lunar landing mission. But the legacy of Apollo 11 would continue to resonate for generations. It was a reminder of the power of human aspiration, the value of exploration, and the ability of people from all walks of life to come together to achieve greatness. The moon landing was not just a triumph of technology, it was a triumph of the human spirit. Armstrong, Aldrin, and Collins had succeeded not only in reaching the moon, but in inspiring the world to look beyond Earth's limits and to dream of the impossible. Apollo 11 had proven that humanity was capable of reaching for the stars, and that the journey of exploration was just beginning. The aftermath of Apollo 11's successful moon landing reverberated throughout the world, marking not only the conclusion of a historic achievement, but also the beginning of a new era in space exploration and human endeavor. The significance of the mission stretched far beyond the immediate triumph of landing on the lunar surface. It was a testament to the collective will of humanity to conquer the unknown and to push the boundaries of what was possible. The immediate aftermath of Apollo 11 was a time of celebration and reflection. In the United States, the moon landing was met with widespread joy and pride. It was the fulfillment of President John F. Kennedy's vision, a promise made in 1961 to land a man on the moon by the end of the decade. Kennedy's dream had become a reality, and his vision, combined with the dedication of thousands of scientists, engineers, astronauts, and politicians, had culminated in a moment that would be remembered for generations. For the astronauts of Apollo 11, the return to Earth was a time of heroism and recognition. Neil Armstrong, Buzz Aldrin, and Michael Collins were hailed as heroes, not only in the United States but around the world. The images of Armstrong's first steps on the moon, the flag being planted, and the photographs taken on the lunar surface were broadcast globally, making the entire planet feel a part of this historic achievement. Armstrong and Aldrin were welcomed home as the first humans to walk on the moon, their achievement marked with parades, speeches, and ceremonies that celebrated their bravery and skill. In contrast, Michael Collins, who had remained in lunar orbit, was often overlooked in the frenzy of admiration for Armstrong and Aldrin. However, his contribution was equally critical, and he would later be recognized for his quiet but essential role in the mission. Globally, the moon landing sparked a wave of wonder and inspiration. Fame. The achievement had transcended national borders, becoming a moment of unity in a world that was often divided by conflict. People from all corners of the Earth watched the event unfold, sharing in the awe and excitement of this extraordinary accomplishment. The landing on the moon was seen not just as a victory for the United States, but as a victory for humanity. It was proof that, regardless of nationality, people shared a common desire to explore and understand the universe. The long-term impact of Apollo 11 extended far beyond the immediate celebrations. The technological advancements that were developed in the process of reaching the moon would have lasting effects on science, engineering, and other fields. The innovations in spacecraft design, navigation, communications, and life support systems that were developed for the Apollo missions laid the groundwork for future space exploration and satellite technology. The lessons learned from Apollo 11's mission and the subsequent missions in the Apollo program also formed the foundation for future human spaceflight endeavors, including the Space Shuttle program, the International Space Station, and plans for missions to Mars. Apollo 11 also inspired future generations of scientists, engineers, and astronauts. The sight of human beings walking on the moon fueled the imaginations of countless young people who aspired to follow in the footsteps of Armstrong, Aldrin, and Collins. It demonstrated the power of education, innovation, and determination. The sense of possibility that came from Apollo 11 helped shape the career paths of many individuals, some of whom would go on to make their own contributions to space exploration and scientific discovery. Politically, the success of Apollo 11 provided the United States with a significant advantage in the ongoing Cold War rivalry with the Soviet Union. The moon landing was not only a technological and scientific achievement, but also a political victory. It was a powerful demonstration of American ingenuity and strength, and it came at a time when tensions between the superpowers were at their height. For the Soviet Union, the success of Apollo 11 marked the culmination of a decade-long space race, and despite the U.S. victory, the Soviets continued to push forward with their own space programs, including the development of space stations and unmanned lunar exploration missions. However, while Apollo 11 was a triumph, the aftermath also raised new questions about the future of space exploration. The moon landing was the culmination of a specific political and scientific goal, and after the success of Apollo 11, the focus shifted toward what would come next. While the Apollo missions continued, with Apollo 12 and others following in its footsteps, the excitement of the moon landing began to fade somewhat as the missions became more routine. The public's attention shifted, and funding for space exploration began to dwindle as priorities shifted toward other areas, including the Vietnam War, civil rights struggles, and economic challenges in the 1970s. In the years following Apollo 11, the legacy of the mission would continue to influence space exploration, but it would also spark debate about the future direction of human spaceflight. Some questioned the long-term value of further manned lunar missions, while others argued that the focus should shift toward exploring Mars and beyond. The Apollo program ended in 1972, with the final mission, Apollo 17. But the lessons learned during the Apollo era set the stage for future exploration. The legacy of Apollo 11 extended far beyond the confines of space. It sparked a revolution in thinking and inspired new ideas about what humans could achieve. The moon landing was not just a victory for one country, it was a triumph for the human spirit, demonstrating that when people work together toward a common goal, they can achieve the impossible. The legacy of Apollo 11 continues to influence space exploration today, with plans for future missions to the Moon, Mars, and beyond. The goal that began with Kennedy's vision is far from complete, and the spirit of exploration and discovery that fueled Apollo 11 remains at the heart of humanity's quest to understand the universe. Apollo 11's impact on the world was profound and enduring. It proved that human ambition, determination, and ingenuity could overcome any obstacle and reach for the stars. The moon landing was a defining moment in human history, and its legacy continues to inspire generations to come, showing that, no matter the challenges, the pursuit of knowledge and the desire to explore will always propel humanity forward into the future. The Apollo program, and especially Apollo 11, serves as a powerful reflection of the broader themes that shape human nature, our collective drive for discovery, and the inherent desire to push beyond known limits. The mission represented more than just a technological achievement. It encapsulated the very essence of exploration, resilience, and the pursuit of the unknown. It illuminated the fundamental truths about humanity's relationship with the universe, and the lessons it imparted are still relevant today as we continue to chart our course into the future of space exploration and beyond. One of the most significant themes that emerged from Apollo 11 is the notion of human perseverance in the face of adversity. The journey to the moon was not smooth, and the Apollo program was filled with setbacks, challenges, and moments of doubt. Yet each failure became a stepping stone, an opportunity to learn and improve. The Apollo 13 mission, in particular, highlighted humanity's resilience and ingenuity. When disaster struck, the Apollo 13 crew and the teams at NASA's Mission Control refused to give in. Instead, they collaborated, adapted, and found creative solutions to ensure the safe return of the astronauts. This relentless pursuit of success in the face of danger is a key lesson from the Apollo program that extends far beyond space exploration. It speaks to the core of human nature and our ability to endure, adapt, and innovate. The importance of collaboration and teamwork is another central theme. The success of Apollo 11 was not the result of one person's effort, but a massive collective undertaking that brought together thousands of individuals from diverse fields of expertise. Scientists, engineers, astronauts, politicians, and even the general public played crucial roles in the mission. Each person involved contributed to the achievement in ways both large and small. The coordination between NASA's ground teams, the astronauts, contractors, and international collaborators was a monumental feat. The Apollo program proved that great accomplishments are rarely achieved in isolation. They require collaboration, open communication, and the shared efforts of many working toward a common goal. The success of the moon landing demonstrated that, when unified in purpose, people could achieve extraordinary things. Moreover, Apollo 11 reinforced the idea that exploration and discovery are intrinsic to the human spirit. The desire to explore is not merely about conquering new frontiers or gaining knowledge. It is deeply rooted in our psychological and cultural makeup. Throughout history, humans have explored the unknown, whether it was crossing the seas, climbing the highest mountains, or delving into the depths of the oceans. Space exploration is the next logical extension of that drive. The moon landing captured this essence, demonstrating that our thirst for discovery is a defining characteristic of our species. It reminds us that we are always looking to move forward, to expand our understanding of the universe, and to push the boundaries of what is possible. In this pursuit, however, the Apollo program also raised important questions about the ethics of exploration and the costs of progress. The Apollo missions were a massive undertaking that consumed vast resources, financial, human, and technological. As the world watched in awe as Armstrong set foot on the moon, some questioned whether the tremendous expense of space exploration could be justified, particularly when there were pressing issues on Earth, such as poverty, inequality, and environmental degradation. The debate over the allocation of resources, whether for space exploration or addressing global challenges, continues to this day. While the Apollo program undoubtedly advanced science and technology in ways that benefited humanity, it also prompted reflection on the balance between scientific curiosity and social responsibility. This debate remains relevant in discussions about future space missions and the broader implications of human exploration beyond our planet. Apollo 11 also demonstrated that innovation is born from necessity. The development of the technologies required for the moon landing, advanced spacecraft, navigation systems, life support systems, and more, pushed the boundaries of what was technologically possible. Many of the innovations developed during the Apollo program had far-reaching applications beyond space exploration. The Apollo program spurred advancements in computing, telecommunications, materials, science, and many other fields. Technologies like integrated circuits, satellite communications, and even the development of portable life-saving devices were direct byproducts of the need to solve problems in space exploration. The lessons learned from Apollo have shaped industries and technologies that benefit society as a whole, demonstrating the interconnectedness of scientific progress and human advancement. One of the most inspiring takeaways from Apollo 11 is the reminder that the pursuit of a higher purpose can unite humanity. The moon landing was an event that transcended borders, politics, and ideologies. For a brief moment, the world was united in its awe and celebration of this remarkable achievement. People of all nations watched as Armstrong took his first steps on the moon, sharing in the excitement and joy of the moment. This unity, however fleeting, highlighted the potential for shared goals to bring people together. The success of Apollo 11 serves as a reminder that, in moments of great challenge and discovery, humanity has the capacity to overcome division and work together toward a common good. This is a lesson that continues to resonate in our globalized world, where cooperation across borders is often crucial to addressing the complex challenges we face. The moon landing also illuminated the power of vision and leadership. The success of Apollo 11 was not a random occurrence. It was the result of visionary leadership, particularly from figures like President John F. Kennedy, who set the ambitious goal of landing on the moon. Kennedy's vision rallied a nation and focused its collective efforts toward a singular purpose. Without such leadership, it is unlikely that the Apollo program would have garnered the political and financial support it needed. Similarly, figures like NASA's administrators, engineers, and astronauts played pivotal roles in ensuring that the vision was realized. Visionary leadership in space exploration continues to shape the future of missions to Mars, the Moon, and beyond, as governments and organizations strive to inspire future generations to achieve new heights. Finally, Apollo 11 is a lasting reminder that the human capacity for dream and imagination is boundless. The Apollo mission was not simply about achieving the scientific or technological feat of landing on the moon. It was also about what that achievement symbolized, the realization that humanity could, with effort, reach the stars. It demonstrated the importance of dreaming big and setting audacious goals. The spirit of Apollo 11 lives on today in the ambitions for human settlement on Mars, the search for extraterrestrial life, and the exploration of distant galaxies. It is a reminder that the impossible is only a matter of perspective, and that, with persistence, vision, and imagination, humans can achieve things that once seemed beyond their grasp. In the end, the legacy of Apollo 11 extends far beyond the lunar surface. It continues to inspire, challenge, and teach us about the potential of the human spirit, the importance of collaboration, and the drive to explore. The lessons of the Apollo program, the value of perseverance, the necessity of teamwork, the power of innovation, are timeless and will continue to shape the course of space exploration and human progress for generations to come. The Apollo 11 mission marked an unparalleled achievement in human history, a moment that not only fulfilled the vision of reaching the moon, but also redefined the boundaries of possibility. It stood as a testament to the power of human determination, ingenuity, and collaboration. As Neil Armstrong set foot on the lunar surface, the world collectively recognized that humanity had crossed a threshold. A new chapter in our understanding of the cosmos had begun. The success of Apollo 11 gave birth to a legacy of exploration that continues to shape the future of space missions and inspire future generations. However, the journey did not end with Apollo 11's historic landing. The achievements of the Apollo program opened up new vistas of possibility for human space exploration. As we reflect on the legacy of Apollo, it is crucial to consider what lies ahead. The drive to explore the unknown, to reach farther and deeper into space, continues to propel humanity forward. The lessons learned from the Apollo missions, particularly the advancements in technology, teamwork, and resilience, form the foundation for the future of space exploration. Looking ahead, the next significant milestones in space exploration will build upon the foundation laid by Apollo. The Artemis program, led by NASA, is the most ambitious endeavor in recent years, aiming to return astronauts to the moon and establish a sustainable human presence there by the mid-2020s. Unlike the Apollo missions, which were primarily a race to the moon, Artemis will focus on long-term exploration and utilization of the lunar surface. This will include building the necessary infrastructure to support a permanent presence, including habitats, power generation, and communication systems, with the goal of preparing for future missions to Mars. The exploration of Mars remains a key focus for space agencies around the world. NASA's goal of sending humans to Mars by the 2030s is becoming more achievable with the ongoing development of advanced spacecraft and landing technologies. The challenges are immense, from the long-duration space travel to the need for self-sustaining life support systems. But the prospect of human missions to Mars presents an exciting new frontier in space exploration. The work being done today to understand Mars' geology, atmosphere, and potential for past life is laying the groundwork for eventual human missions that will answer profound questions about life beyond Earth. In addition to NASA's efforts, private companies such as SpaceX, led by Elon Musk, are pushing the envelope of space exploration. SpaceX's Starship program, designed to be a fully reusable spacecraft capable of carrying humans to Mars and beyond, represents a transformative shift in how we approach space travel. The company's success in developing reusable rockets has already reduced the cost of launching payloads into space, and its ambitious plans for interplanetary travel could redefine humanity's relationship with space. The International Space Station, ISS, which has been a remarkable hub for scientific research and international collaboration since its launch, will continue to play a crucial role in human space exploration. Lovias, as NASA, the European Space Agency, ESA, Russia's Roscosmos, Japan's JAXA, and other international partners work together on the ISS, they are laying the groundwork for future deep space missions. The knowledge gained from the ISS about long-term space travel, radiation exposure, and living in space will be critical for missions to the Moon, Mars, and beyond. In addition to the human exploration of distant worlds, robotic exploration will remain essential in the coming decades. The success of robotic missions such as the Mars rovers, the New Horizons mission to Pluto, and the James Webb Space Telescope will continue to provide invaluable data that informs our understanding of the solar system and the broader universe. These robotic missions are pushing the boundaries of what we know, uncovering new mysteries, and preparing the way for human exploration. As we look toward the future, the ethics of space exploration will continue to evolve. The Moon and Mars are not empty, lifeless worlds. They are environments that need to be approached with responsibility and caution. As we move forward with plans for human settlement on the Moon and Mars, there will be a growing need to address concerns about planetary protection, resource extraction, and the long-term environmental impact of human activities in space. The lessons learned from Earth's environmental challenges must be integrated into space exploration efforts to ensure that humanity's expansion into space is sustainable and ethical. Furthermore, the role of international cooperation in space exploration will become even more vital. Space exploration, while often seen through the lens of national pride, is increasingly a global endeavor. As nations collaborate on projects such as the ISS, the Lunar Gateway, and lunar exploration missions, the spirit of collective achievement seen in Apollo 11 continues. The future of space exploration will require collaboration, not competition, as humanity seeks to address global challenges such as climate change, resource scarcity, and technological advancement through the exploration of space. The exploration of space is not just about technological advancement, it is about the growth and evolution of human civilization. Space-based technologies, from satellites to space tourism, are already affecting our daily lives in profound ways. Advances in materials, science, robotics, telecommunications, and artificial intelligence, all born from the necessity of space exploration, have already changed industries ranging from medicine to agriculture to communications. As humanity expands its presence in space, these technologies will continue to have transformative effects on life here on Earth. Ultimately, the future of space exploration is about expanding the horizons of human knowledge and capability. As we venture farther into the cosmos, we will face challenges that will test the limits of our understanding, our technology, and our ability to work together. The legacy of Apollo 11 reminds us that, as a species, we are capable of achieving great things when we dream big, work together, and persevere in the face of adversity. The exploration of space is not just a pursuit of scientific discovery. It is an expression of humanity's curiosity, ambition, and desire to push beyond the boundaries of the known world. As we look to the stars and plan for future missions, we must remember the spirit of Apollo 11, that with vision, determination, and collaboration, there are no limits to what we can achieve. The journey that began with the moon landing is just the beginning. The next chapter in humanity's story will take us to Mars, to the farthest reaches of our solar system, and perhaps one day to other star systems. The adventure is far from over, and the possibilities are as vast as the universe itself. The year is 2035, and humanity stands on the precipice of an era unlike any before. The global community, while still grappling with the complex challenges of Earth climate change, resource scarcity, and political tensions, finds itself united by a singular goal: the exploration and potential colonization of distant star systems. For centuries, humanity had gazed up at the stars, wondering what lay beyond the limits of their own solar system. Now, after decades of scientific discovery, technological advancements, and political collaboration, that dream was beginning to take shape. The mission at hand was nothing short of extraordinary: interstellar travel. The dream of traveling between the stars had been a topic of speculation and theoretical exploration for as long as humanity had understood the vastness of the universe. The Cold War era had given birth to an intense space race, where political and military powers sought to reach the farthest frontiers of space for both prestige and security. The subsequent decades saw space exploration take on a more collaborative and scientific role, but the desire to break free from the constraints of the solar system had remained an elusive goal. This new mission, however, was different. It wasn't just about planting a flag on another planet or moon within the solar system. It wasn't merely about exploration for the sake of discovery. This mission was about the survival and future of humanity itself. The pressing issues of Earth overpopulation, dwindling resources, and environmental collapse had given rise to the idea that the long-term solution might lie among the stars. To ensure the survival of the species, humanity would need to find new worlds, new frontiers that could support life. The fate of Earth and the future of the human race were intertwined with the success of this mission. At the center of this new space race was a coalition of nations and private organizations that had come together with the singular purpose of developing the technology necessary for interstellar travel. The concept was clear. Humanity needed to find a way to traverse the vast distances between stars in a reasonable amount of time. With current technology, the journey to even the closest stars would take thousands of years, far beyond the lifespan of any spacecraft or human traveler. The only way forward was to push the boundaries of physics itself and find ways to manipulate space-time, utilize antimatter, or even harness the power of black holes. The challenges were immense, but the rewards, if successful, would change the course of human history. The stakes were high. Failure would mean not only the abandonment of humanity's future in the stars, but also the loss of what had become one of the most ambitious and globally supported projects in history. The political and social pressures were enormous. Governments around the world, grappling with their own issues, now had to find a way to prioritize interstellar research while balancing the needs of their own people. The economic costs of the mission were astronomical, and the political ramifications of such a monumental undertaking would affect global relations for generations to come. Key figures in this effort included world leaders, visionary scientists, engineers, and astronauts. They were the dreamers and the doers, the ones willing to take humanity's greatest leap into the unknown. Their leadership and expertise would be tested every step of the way. This mission was not just about technological innovation, it was about inspiring humanity to reach for the stars and to believe that the impossible could become possible. As the world looked to the stars, the mission to achieve interstellar travel became more than just a project. It became a symbol of human potential, resilience, and the universal desire to explore. The historical context of this mission was rich with layers of societal, technological, and political developments that had laid the groundwork for such an ambitious endeavor. It was a culmination of the space programs that began during the Cold War, with the space race between the United States and the Soviet Union, where each side sought to assert their dominance in space through milestones such as the launch of Sputnik, the first human in space, and the Apollo 11 moon landing. The space race had fostered innovation, ignited curiosity, and created a competitive spirit that fueled advancements in technology, science, and engineering. In the decades that followed, the exploration of space became more about scientific discovery and international cooperation than about political rivalry. The establishment of the International Space Station, ISS, in 1998 marked a turning point, where nations worked together to conduct experiments in space, study the effects of long-term spaceflight on the human body, and explore the potential for human settlements beyond Earth. These collaborations, along with advancements in robotics, artificial intelligence, and propulsion technology, set the stage for humanity's next leap, the possibility of traveling between stars. The new era of interstellar travel also came at a time when technology had advanced to the point where the theoretical concepts, once considered science fiction, were beginning to look more like plausible solutions. Concepts such as the Alcubierre drive, a theoretical faster-than-light propulsion system based on a form of warp drive, and antimatter propulsion, were being explored by the brightest minds in physics and engineering. Research into fusion energy had reached new heights, and space agencies were beginning to focus on harnessing the power of black holes or wormholes to shorten the travel time between distant stars. The mission was still in its infancy, with the basic science and theories in development. However, the financial investment and political will to support this ambitious goal were evident. The mission was not only about the science, it was about the future, and as humanity stood on the edge of this monumental leap, the eyes of the world were fixed on what would come next. As we move forward into the story of interstellar travel, we will explore the challenges that these pioneers faced, the technological barriers, the skepticism of society, the political pressure, and the immense risks involved in such an unprecedented undertaking. But we will also look at the vision that drove them, the leadership that inspired them, and the discoveries that would pave the way for humanity's greatest journey, the journey to the stars. In the early days of the mission to develop interstellar travel, the challenges seemed insurmountable. Despite the rapid advances in space technology during the 21st century, the leap from exploring our own solar system to traveling between the stars was an order of magnitude greater in terms of technological, political, and social obstacles. The very notion of interstellar travel posed questions that were as much philosophical as they were scientific. Could humanity ever truly leave the confines of the solar system, or was it bound forever to the blue orb we called? This challenge, however, was not a deterrent. It was the spark that ignited the mission. At the heart of the mission was the visionary leadership of political figures, scientists, and engineers who saw the potential not only to explore new worlds, but to ensure the long-term survival of humanity. It was a vision born out of necessity. As Earth's population continued to grow, climate change threatened the planet's ecosystems, and the Earth's resources dwindled. Leaders across the globe, sensing the urgency of the moment, understood that the future of humanity was linked to the stars. If humanity was to secure a future beyond Earth, it would need to become a multi-planetary species. And that meant developing the technology to travel to other star systems. The technological limitations in the early stages were formidable. Current space travel was constrained by the vast distances between stars. The closest star system to our own, Alpha Centauri, was over 4.3 light-years away. At the speed of light, it would take over 4 years to reach it, something far beyond the capabilities of existing propulsion systems. Even with the most advanced chemical rockets, journeys to even the closest stars would take tens of thousands of years. For interstellar travel to become a reality, scientists and engineers knew that they would need to rethink the fundamentals of physics itself. The first theoretical breakthrough came from a new interpretation of Einstein's theories of relativity. The Alcubierre drive, a theoretical concept proposed by physicist Miguel Alcubierre in 1994, suggested that it might be possible to bend space-time, effectively allowing a spacecraft to travel faster than the speed of light without violating the laws of physics. By contracting space in front of the ship and expanding it behind, a spacecraft could ride a wave of space-time, allowing it to traverse vast distances almost instantaneously. While this idea sounded like science fiction, it was based on rigorous mathematical models, and physicists began to consider it as a possible avenue for future exploration. However, the major hurdle remained. How could such a phenomenon be achieved in practice? The amount of energy required to warp space-time on a scale large enough for human travel was astronomical, far beyond the capacity of any energy source humanity had at the time. This problem led to intense debate within the scientific community, with some proposing radical new ideas, such as harnessing antimatter for propulsion. Antimatter, when it interacts with matter, releases vast amounts of energy, and if controlled, it could provide the propulsion needed for interstellar journeys. The challenge, of course, was in producing and storing antimatter, which was a highly complex and costly process. The development of fusion energy, which had been progressing steadily throughout the 21st century, provided another potential path. Fusion power, the process that powers the stars, was seen as a key element in the development of the propulsion systems required for interstellar travel. Harnessing fusion for space travel would provide nearly unlimited energy, but the challenge was in creating a sustainable and controllable fusion reaction. The first major breakthrough in fusion technology came with the successful operation of a fusion reactor in the 2030s, though it was still in its infancy. In parallel, solar sails were also explored as a more immediate, though still impractical, solution. By using the pressure of sunlight to propel spacecraft, solar sails could allow for long-distance travel without the need for fuel. Though not capable of interstellar travel in the short term, solar sails were seen as a stepping stone, potentially useful for missions within the solar system, and as a part of a broader strategy to develop more advanced technologies. Despite the promising theoretical breakthroughs, there was a growing sense of societal skepticism. Many viewed interstellar travel as a foolhardy pursuit, an expensive, unproven venture that distracted from more immediate concerns on Earth. As the Earth's population grew and resources became scarcer, governments and citizens alike struggled to balance the desire for exploration with the pressing needs of the planet. Critics of the interstellar program pointed out that the immense cost of developing such technology might be better spent addressing issues like poverty, global warming, and inequality. But the visionaries in charge of the mission saw these challenges not as obstacles, but as reasons to push forward. The belief that humanity's future could not solely depend on a single planet, especially one facing such tremendous challenges, drove the mission's leadership to rally global support. The visionary speeches, akin to John F. Kennedy's famous 1961 Moon speech, were crucial in gathering the international support needed for such a colossal undertaking. The promise of a new frontier, of worlds beyond our own, became a rallying cry that captured the imagination of the global public. Governments, recognizing the political and scientific importance of the project, began to commit unprecedented resources to interstellar research. A significant turning point came in 2032, when a global summit was held in Geneva, bringing together representatives from the United States, China, the European Union, Russia, other spacefaring nations. For the first time in history, space agencies from around the world agreed to collaborate on a single mission: the development of interstellar travel. A joint effort, dubbed Project Starbound, was initiated, with the goal of developing the first spacecraft capable of reaching another star system within the next 50 years. The collaboration was a monumental shift in the way space exploration was conducted, moving away from competition and toward international cooperation. The political, social, and economic pressures on the project were enormous. The mission to reach the stars was not just about scientific achievement, it was about the future of humanity. The project had to succeed, not just for the technological innovations it would bring, but for the hope it would instill in a world grappling with its own survival. The question of whether humanity could overcome its own limitations, whether it could survive beyond the cradle of Earth, became a central theme in the early days of the mission. It was no longer just about the technology, it was about survival, about the potential to build a future in the stars. As the mission began to take shape, the initial technological, political, and societal obstacles began to transform into opportunities. Through global cooperation, breakthroughs in science, and the determination of a new generation of dreamers, humanity began to turn its focus toward the stars. The vision was clear. Interstellar travel was no longer just a dream, but a challenge that humanity would rise to meet. The road ahead would be difficult, but it was a road worth traveling. The dream of reaching the stars was no longer science fiction, it was becoming science fact. The journey toward interstellar travel was not a solitary endeavor. It was shaped by the efforts of countless individuals, scientists, engineers, astronauts, and leaders, whose visions, expertise, and determination were integral to the mission's progress. Each person brought a unique set of skills and ideas, and together they formed the backbone of the mission that aimed to take humanity beyond the stars. Their stories, full of ambition, struggle, and triumph, provide a human face to the grand, technological undertaking that would one day be remembered as a turning point in the history of exploration. At the heart of the project stood Dr. Elena Ramirez, an astrophysicist whose groundbreaking work on space-time manipulation helped form the theoretical basis for the mission. She was the intellectual driving force behind the development of the Alcubierre drive, working tirelessly with a team of physicists to test its feasibility. Her early theories, considered highly speculative by many in the scientific community, became the cornerstone upon which much of the interstellar propulsion work was built. Dr. Ramirez's ability to blend theoretical physics with practical engineering was key to the mission's success, and her vision of interstellar travel inspired a generation of scientists to believe that what was once thought impossible could become a reality. Dr. Ramirez's work was not done in isolation. She was supported by a dedicated team of engineers, mathematicians, and physicists, many of whom had to rethink everything they knew about propulsion and energy. A key member of her team was Zhao Wei, a brilliant engineer whose innovations in fusion energy helped make the practical use of the Alcubierre drive a reality. Zhao's work on harnessing the immense power required for space-time manipulation led to the development of the hyperfusion reactor, an energy source that was powerful enough to fuel the interstellar propulsion system. Zhao's work was considered a breakthrough in energy production, and his contributions helped bridge the gap between theory and practice. While Dr. Ramirez and Zhu Hao focused on the theoretical and engineering aspects, General Adrian Kingston played a crucial role in rallying support for the mission. As the head of the International Space Exploration Coalition, ISCC, General Kingston was the political and organizational leader who convinced governments and private enterprises to pool resources for the project. His ability to navigate the complex political landscape, forging alliances between nations with differing priorities, was crucial in ensuring that the mission was not just a national effort but a global one. General Kingston's experience in military operations and leadership was key in organizing the vast, multinational team that would be needed to tackle the monumental task of interstellar travel. The teamwork among the various countries and organizations that formed the backbone of the mission was remarkable. At the forefront of this cooperation was Dr. Anna Dupont, the French aerospace engineer who led the construction of the Starbound Orbiter, the spacecraft designed to be humanity's first interstellar vessel. Dr. Dupont's reputation as an expert in spacecraft design made her the perfect candidate for the job, but the task ahead was far from easy. The spacecraft had to be designed to withstand the extreme conditions of deep space, and it had to be equipped with the necessary systems to support a crew for a journey that could take decades. Her work was not only about designing a ship, it was about designing a self-sustaining system capable of supporting human life for extended periods. Dr. Dupont's innovative designs, including advanced life support systems, radiation shielding, and propulsion mechanisms, would become the blueprint for the spacecraft that would one day journey to the stars. In addition to Dr. Dupont, a team of astronauts was assembled, individuals who would be tasked with traveling beyond the solar system and ensuring the safety of humanity's first interstellar voyage. One of the most prominent among them was Captain Marcus Hughes, a seasoned astronaut with a reputation for his calm under pressure and his ability to lead in the most extreme environments. Captain Hughes was chosen to lead the first interstellar crew due to his experience in long-duration space missions and his unmatched ability to handle the challenges of space travel. He was the ideal candidate for the mission's most demanding role, to navigate humanity's first journey to another star system. Alongside Captain Hughes was Dr. Naomi Patel, a biologist whose expertise in space medicine and human adaptation to long-term space travel was essential to the mission's success. Dr. Patel's job was to ensure that the crew remained healthy, both physically and mentally, during their years-long voyage. Her research into the effects of microgravity, radiation, and isolation on the human body provided critical insights into how to keep astronauts in peak condition while away from Earth for extended periods. Dr. Patel was also tasked with studying how the crew would handle the psychological toll of interstellar travel, ensuring that they remained motivated and mentally strong throughout the journey. The mission also required a diverse team of engineers who specialized in everything from artificial intelligence, AI, to quantum computing. Samuel Nguyen, a brilliant programmer and AI expert, was responsible for developing the onboard AI system that would assist the crew in navigation, communication, and daily operations. Nguyen's work on AI-driven automation would prove invaluable, as it allowed the crew to focus on more critical tasks while the AI handled routine operations and decision-making processes. This combination of human expertise and artificial intelligence would be key to making the mission viable, as it ensured that the ship would run smoothly even during the most challenging phases of the journey. In addition to the core team, the Starbound mission was supported by thousands of engineers, technicians, and specialists from around the world. Every aspect of the mission, from propulsion to communication, from life support to navigation, required the input of countless individuals who worked tirelessly behind the scenes. Many of these experts were part of the space agencies that had participated in previous space exploration missions, and their collective knowledge and experience were invaluable to the interstellar mission. The mission's progress was also deeply influenced by global collaboration. particularly with private space exploration companies. Celestial Ventures, a private corporation founded by visionary entrepreneur Jonathan Carrington, played a critical role in the development of the spacecraft's propulsion system. Carrington's company had been at the forefront of the commercial space industry for years, and its involvement in the interstellar mission demonstrated the growing role of private companies in space exploration. The partnership between public space agencies and private corporations ensured that the resources needed for such an ambitious project were made available. In the early stages of the mission, there were many doubters, both inside and outside the scientific community, who questioned the feasibility of interstellar travel. The project faced significant skepticism, with critics pointing to the enormous technological challenges, the astronomical costs, and the uncertainty of success. But the leadership of Dr. Ramirez, Zhao, General Kingston, Dr. DuPont, and their team, along with the global support of governments and private enterprises, pushed through these doubts. Their belief in the vision, in the future of humanity beyond Earth, and in their ability to overcome the unimaginable obstacles ahead became the driving force behind the mission. The individuals who led the way in the development of interstellar travel were not just pioneers in their fields. They were also symbols of humanity's ability to dream, to innovate, and to work together toward a common goal. Their determination, skills, and shared vision would ultimately change the course of human history, taking the first steps toward a future where the stars were no longer distant, unreachable points in the sky, but destinations within humanity's reach. The mission to achieve interstellar travel required not only a shift in the understanding of physics, but also groundbreaking advancements in technology. Over the course of several decades, humanity would confront immense challenges and make remarkable strides in a variety of fields: propulsion, energy, spacecraft design, artificial intelligence, and more. The breakthroughs that emerged during this period would not only enable humanity to reach other star systems, but would also reshape industries, change the way we think about space, and redefine what it meant to be an interplanetary species. The first significant breakthrough came in propulsion. The idea of traveling faster than the speed of light had long been dismissed as science fiction. However, with the development of the Alcubierre drive, a theoretical concept based on the manipulation of space-time, the possibility of faster-than-light travel became a real pursuit. The drive essentially created a warp bubble around a spacecraft, contracting space in front of it and expanding space behind it. This would allow the spacecraft to move faster than light, bypassing the relativistic limits of conventional travel. However, there was a major hurdle. The amount of energy required to create such a warp bubble was far beyond the capabilities of existing power sources. This issue was resolved by a series of incremental advancements in fusion energy. By the 2030s, humanity had successfully created controlled, sustainable fusion reactions that provided an almost limitless source of power. The breakthrough came with the development of the hyperfusion reactor, which utilized hydrogen isotopes like deuterium and tritium to generate immense amounts of energy. This fusion reactor was compact enough to be integrated into spacecraft and powerful enough to fuel the Alcubierre drive, making the concept of faster-than-light travel a possibility. The hyperfusion reactor became the cornerstone of the interstellar spacecraft, capable of generating the energy required to manipulate space-time and propel the spacecraft across vast distances. The implementation of fusion energy in spacecraft also required advancements in energy storage and shielding. The tremendous amounts of energy produced by the fusion reactor had to be safely stored and distributed throughout the spacecraft. To solve this, scientists developed quantum batteries, which could store vast amounts of energy in compact spaces, allowing for efficient energy management during long-term travel. Along with this, radiation shielding was developed to protect the spacecraft from the high-energy particles and radiation that would be encountered in deep space. Advanced materials, including graphene composites and nanostructured alloys, were used to build the hulls of spacecraft, providing them with the necessary durability and protection against the harsh environment of space. Another key technological breakthrough came in spacecraft design. The first interstellar spacecraft, the Starbound Orbiter, required an entirely new approach to engineering. The spacecraft had to be capable of sustaining human life for extended periods, potentially decades, while also carrying the necessary supplies, equipment, and research instruments. Traditional spacecraft designs, which were based on missions within the solar system, were simply too small and inefficient for long-distance interstellar travel. The Starbound orbiter was designed to be a self-sustaining ecosystem, featuring advanced life support systems that could recycle air, water, and food. The spacecraft utilized closed-loop systems, meaning that every resource could be reused, minimizing waste and the need for constant resupply. The habitat areas were equipped with artificial gravity, generated by rotating sections of the spacecraft, to keep the crew healthy and combat the effects of prolonged exposure to microgravity. The ship was divided into several sections, including a research and operations section, a living quarters area, and a hydroponics garden to provide fresh food. The hydroponics system used advanced aeroponic techniques to grow crops in a low-gravity environment, ensuring that the crew would be self-sufficient during their long journey. In addition to these innovations, the spacecraft also featured advanced AEI systems that played a critical role in the mission's success. The Starbound AEI, designed by Samuel Nguyen, was responsible for managing the spacecraft's systems, including navigation, life support, and communication. The AEI was equipped with self-learning algorithms, allowing it to adapt to unexpected challenges and optimize the spacecraft's systems for efficiency. The AE also helped monitor the crew's health, providing real-time medical advice and maintaining a balance between work, rest, and recreation. The integration of AI was essential in reducing the mental strain on the crew, allowing them to focus on their mission rather than daily tasks. Another significant breakthrough was in the area of deep space navigation. To travel to other star systems, the spacecraft needed an advanced navigation system capable of pinpointing its position with incredible precision. The introduction of quantum entanglement in communication and navigation systems allowed for near-instantaneous data transfer over vast distances. Quantum entanglement, which had been theorized for decades, was finally harnessed to create an advanced navigation system that used entangled particles to communicate with ground stations and other spacecraft in real time. This system allowed the spacecraft to adjust its course quickly and accurately, ensuring that it remained on track even as it traveled farther from Earth. While propulsion, energy, and spacecraft design were at the forefront of technological advancements, other innovations played critical roles in the mission's success. The development of autonomous robotics and remote-controlled drones revolutionized the way interstellar missions were conducted. These robots were used to explore distant, celestial bodies, perform repairs on the spacecraft, and assist in scientific research. Their ability to operate autonomously, without direct human intervention, allowed the crew to focus on their mission, while the robots handled routine tasks and performed experiments that would have been impossible for humans to carry out in such remote locations. Communication was another area that required significant breakthroughs. The vast distances involved in interstellar travel meant that traditional communication methods, reliant on radio waves, would be far too slow for real-time exchanges. Researchers developed subspace communication systems that used a newly discovered form of communication that could bypass the limitations of light-speed transmission. Subspace communication allowed for near-instantaneous contact with Earth and other ships, enabling the crew to maintain contact with mission control and ensure the success of the mission. Along with these advancements, new material sciences played a crucial role in the development of the spacecraft and its systems. The research into nanomaterials, carbon nanotubes, and superconducting materials allowed for the creation of lighter, stronger, and more efficient components. These materials were used in everything from the spacecraft's hull to its propulsion systems, ensuring that the spacecraft could withstand the harsh conditions of deep space while maintaining the necessary functionality to carry out its mission. The combination of these technological breakthroughs, fusion energy, space-time manipulation, AI, autonomous systems, and cutting-edge materials, created the foundation for humanity's first interstellar spacecraft. These innovations, each a significant leap forward in their respective fields, brought humanity closer to the reality of reaching the stars. They were a testament to the creativity, resilience, and determination of the individuals and teams who had worked tirelessly to make the impossible possible. The success of these breakthroughs was not just a victory for the scientific and engineering communities. It was a symbol of what humanity could achieve when it combined its intellect, imagination, and collective will. The interstellar mission was no longer a distant dream. It was becoming a tangible reality, with each breakthrough pushing humanity further into the unknown. The journey to achieve interstellar travel wasn't a single event, but a series of milestones, each one a test of humanity's commitment, perseverance, and ability to adapt. From the conceptual stages to the construction of the spacecraft, and finally the launch and eventual journey beyond the solar system, each phase of the mission was marked by pivotal events that tested the limits of science, engineering, and human resolve. These key missions and events, full of triumphs, obstacles, and dramatic turns, laid the foundation for the greatest adventure in human history, the journey to the stars. The first major mission of the interstellar program was the construction and testing of the Starbound Orbiter, the spacecraft that would carry humanity's first interstellar crew beyond the solar system. The design and assembly of the spacecraft took nearly 2 decades, involving countless engineers, architects, scientists, and astronauts. The process was painstakingly detailed. Each system was tested rigorously to ensure it could withstand the extreme conditions of deep space. But the journey to build the ship was not without its complications. The immense size of the spacecraft, designed to house a crew for decades, and its numerous systems, from life support to propulsion, presented challenges no one had ever faced before. It became clear that the mission would require not just technical expertise, but a new kind of thinking, one that could address unforeseen challenges in space travel. The first test flight of the Starbound Orbiter, known as Mission Starbound 1, was scheduled to take place in 2045. It was intended to be a precursor to the eventual interstellar journey, testing the spacecraft's propulsion, navigation, and communication systems, as well as its ability to operate independently for extended periods. The mission's goal was not to leave the solar system, but to push the limits of human space travel to a point where the team could verify that the technology worked as intended. As the day of the launch approached, anticipation was at an all-time high. Mission Control in Geneva, the heart of the project, was alive with activity. The launch of Mission Starbound 1 would be the first step toward achieving what had once been deemed impossible interstellar travel. The crew consisted of a select group of astronauts and scientists, led by Captain Marcus Hughes, who had been chosen for his leadership experience and calm under pressure. They were tasked with testing the spacecraft's capabilities, including the newly developed Alcubierre drive powered by the hyperfusion reactor. The launch went off without a hitch. For the first time, the ship's warp drive system was activated, generating a small-scale warp bubble around the spacecraft. The sensation inside the spacecraft was unlike anything the crew had ever experienced. For a brief moment, the laws of physics seemed to bend, and the ship was propelled at speeds unimaginable to previous generations. While the mission did not aim for interstellar travel, it marked the first time that humanity had created a viable means to travel beyond the confines of the solar system. However, the success of Mission Starbound 1 did not come without its problems. During the mission, the spacecraft experienced an unexpected energy surge that caused a temporary system failure. The team had to work quickly to resolve the issue before it endangered the ship's operation. This incident, though minor in comparison to the overall success of the mission, highlighted just how difficult and unpredictable space travel could be, especially on such an unprecedented scale. Despite the scare, the crew successfully completed the mission and returned to Earth, confirming that the spacecraft's propulsion systems were operational and ready for future missions. The success of Mission Starbound 1 set the stage for Mission Starbound 2, which was intended to be the first interstellar probe launched beyond the solar system. While the goal was not to carry human passengers, the spacecraft was equipped with advanced sensors and equipment to gather data on the outer regions of space and test the capabilities of the spacecraft's warp drive over longer distances. The mission also carried an experimental AI system designed to simulate the conditions of a long-term human journey, analyzing everything from human health to resource management. Mission Starbound 2 was launched in 2049. The spacecraft would travel beyond the orbit of Neptune, using its warp drive to traverse the vast distances of the outer solar system and begin its journey toward the Alpha Centauri star system. The mission was a success in many ways, pushing the boundaries of our ability to travel and communicate across vast distances. However, during the mission, the crew encountered another unexpected challenge. A massive radiation storm that had the potential to disrupt the spacecraft's communication systems and power supply. The storm had not been detected in advance, and its intensity caused a temporary failure in the spacecraft's communication systems, forcing the crew to rely on backup systems and manual intervention to maintain stability. Despite these complications, the mission returned valuable data, confirming that deep space navigation and interstellar travel were indeed possible. The Starbound 2 probe had passed through the outer reaches of the solar system, successfully utilizing the warp drive for the first time in practical conditions. The data gathered from this mission would be used to refine the warp drive technology, ensuring that it was safe and reliable for future manned missions. By 2055, humanity was ready for its most ambitious mission to date, Mission Starbound 3, the first interstellar crew mission beyond the solar system. This would be the first time humanity sent a team to another star system. The crew, led by Captain Hughes, would leave Earth on a journey to Alpha Centauri, the closest star system to our own. The mission's goal was not only to test the ability of humans to survive on an interstellar journey, but to conduct scientific research on the planets around Alpha Centauri, including potential habitable zones. For humanity, this mission represented the culmination of decades of work, and it marked a critical turning point in the quest for space exploration. The launch of Mission Starbound 3 was a momentous occasion. The spacecraft, now fully equipped with advanced systems for navigation, life support, and energy production, was ready for the long journey. The ship's warp drive would carry the crew to Alpha Centauri in just a matter of months, an astronomical leap compared to the thousands of years it would take with conventional propulsion. However, just days before the mission's scheduled launch, an unexpected solar flare erupted from the sun. The flare, massive in scale, sent a burst of radiation toward the spacecraft, potentially jeopardizing the mission's success. The mission was delayed as engineers worked around the clock to protect the spacecraft from the solar flare's effects. The flare's intensity was higher than anticipated, and there was real fear that the mission might have to be postponed indefinitely. The crew, now familiar with the unpredictable nature of deep space exploration, remained calm under pressure. Captain Hughes, who had led previous missions, worked closely with Mission Control to assess the damage and find a way to shield the spacecraft's vital systems from the radiation. After several tense days, the spacecraft was deemed safe for launch, and the mission resumed. When Mission Starbound 3 finally launched in 2056, the world watched in awe. The spacecraft's Alcubierre drive was activated once again, and the crew embarked on their historic journey to Alpha Centauri, ready to face whatever challenges awaited them. This mission would test everything humanity had learned about interstellar travel, and it would ultimately determine whether the dream of traveling to the stars could truly be realized. As the spacecraft traveled farther from Earth, the crew's experience in space began to change them. The isolation, the vast distances, and the passage of time began to take their toll. The mission's emotional and psychological challenges became as important as the technological hurdles. The crew faced moments of doubt, but the shared sense of purpose kept them focused. They knew that their success or failure would shape the future of humanity. The missions leading up to this point had not only been technical triumphs, but also emotional and psychological journeys. The milestones along the way were not just about reaching new destinations, but about overcoming the obstacles that lay in both the vastness of space and the limits of human endurance. Each mission, each success and failure, brought humanity one step closer to realizing the ultimate goal, becoming an interstellar species. No journey, especially one as ambitious and far-reaching as interstellar travel, is without its crises. While the early missions that led humanity to the brink of the stars were marked by innovation and triumph, they also highlighted the fragility of the endeavor. The vastness of space, the complexity of the systems, and the uncertainties of human adaptation to long-term space travel presented challenges that no one could have predicted. The true test of humanity's commitment to this mission would come not in its successes, but in how it responded to its failures and crises. The most significant crisis in the early days of interstellar exploration occurred during Mission Starbound 3, humanity's first crewed journey to Alpha Centauri. The mission had been meticulously planned, but as the spacecraft journeyed farther into deep space, it became clear that even the most advanced technology could not shield the crew from the unpredictable dangers of space. As the spacecraft approached the halfway point of its journey, something went terribly wrong. It began with a critical failure in the life support system. The system, designed to recycle air and water while maintaining a stable atmosphere, began to malfunction. At first, the problems were minor, a slight dip in oxygen levels, a fluctuation in temperature. But over the course of several days, these issues grew worse. The crew, though trained for emergencies, found themselves facing a problem they had not anticipated. Captain Marcus Hughes, already a seasoned leader of previous missions, quickly recognized the magnitude of the crisis. The life support system failure threatened not only the success of the mission, but the survival of the crew. The systems designed to purify air, filter waste, and maintain water levels were all beginning to break down, and the spacecraft was deep in uncharted space, far from Earth and beyond the reach of rescue. The crew was on their own, with only their training, resourcefulness, and determination to guide them. The decision to go into emergency mode was immediate. The crew isolated the damaged sections of the spacecraft and began to manually work on restoring key systems. Dr. Naomi Patel, the mission's biologist and medical expert, immediately began to assess the impact of the malfunction on the crew's health. Without the proper balance of oxygen, temperature, and water, the crew would begin to experience the physical and psychological effects of prolonged exposure to harsh conditions. It became clear that there was no quick fix. The hyperfusion reactor that powered the spacecraft was functioning properly, but the life support systems at the heart of the spacecraft's sustainability were damaged beyond immediate repair. The crew was faced with the realization that they would have to rely on the backup systems designed for short-term crises, systems that had never been intended for the scale and duration of this particular emergency. The crew worked tirelessly around the clock, using parts from less critical systems and improvising with materials they had on board. They managed to create a temporary solution to stabilize the spacecraft's life support. It was a monumental task that required everyone on board to contribute, not just as specialists in their fields, but as problem solvers in the most dire of circumstances. During the crisis, tensions ran high. The psychological toll of isolation, the fear of failure, and the uncertainty of their future weighed heavily on the crew. Dr. Patel, who had spent years researching the effects of space travel on the human body, now had to apply her knowledge in real time, monitoring her crew for signs of psychological strain, physical deterioration, and fatigue. The vast emptiness of space seemed to close in on them, and each passing day without full system recovery heightened the sense of isolation. However, the team's response to the crisis was nothing short of extraordinary. While they faced mounting pressure, they demonstrated resilience and determination, refusing to give in to panic. Captain Hughes maintained his leadership role, ensuring that the crew remained calm, organized, and focused on their task. His leadership style, which had always been characterized by steady resolve, proved indispensable in guiding the crew through their darkest moments. Meanwhile, Xiao Wei, the mission's lead engineer, worked tirelessly with the crew to troubleshoot and repair the life support systems. Zhao's quick thinking and deep knowledge of the spacecraft systems allowed him to find workarounds that kept the ship functioning, even when conventional methods failed. He and his team of engineers implemented a multi-step repair process that, while far from perfect, gradually stabilized the spacecraft systems, allowing the crew to breathe easier, literally and figuratively. But even as the crew worked on repairing the ship, the emotional toll began to show. General Adrian Kingston, overseeing the mission from Earth, was constantly in communication with the crew, offering support and guidance, but the distance was palpable. The inability to physically intervene, to offer direct assistance, created a sense of helplessness on both sides. This isolation tested the emotional strength of the crew as they faced the stark reality that they were alone in the void. As the crisis stretched on, the crew began to experience the psychological effects of the extended ordeal. Though the immediate physical dangers were largely mitigated, the mental strain began to take its toll. Long periods of silence, disrupted sleep cycles, and the overwhelming pressure of knowing that failure could mean the end of their journey. These factors weighed heavily on the astronauts. Dr. Patel's expertise in space medicine became even more crucial. As she monitored the crew's mental health, and ensured that they stayed mentally sharp and emotionally stable. The breakthrough came after several weeks of intense effort. Using a combination of experimental techniques and innovative fixes, the crew managed to restore the life support system to full functionality. It was not the perfect solution they had hoped for, but it was enough to allow them to resume the journey, now with a renewed sense of determination. The crisis had not only tested their technical skills, but also their character. Each crew member had proven their mettle, and their ability to face adversity head-on had solidified the bond between them. As the crew slowly recovered from the crisis, the psychological and emotional scars remained. The solitude of deep space became even more pronounced, with the crew members often reflecting on their own fragility, the vastness of the universe, and humanity's place in it. Yet, in the face of adversity, the crew's resilience and unity had made them stronger, both as individuals and as a team. The crisis had shown the world that interstellar travel was not without its risks. It demonstrated that the technological challenges, while monumental, were not the only hurdles. The emotional and psychological toll of such long-duration missions was just as critical to consider, but it also proved that, even in the face of catastrophic challenges, humanity had the ability to adapt, innovate, and overcome. The success of mission Starbound 3, despite the crisis, would go down in history as a pivotal moment, not only for interstellar travel, but for humanity's enduring spirit in the pursuit of discovery. The lessons learned during the mission would shape the future of deep space exploration, paving the way for more ambitious endeavors and ensuring that future missions could face and overcome similar challenges. After years of painstaking preparation, technological breakthroughs, political collaboration, and overcoming significant crises, humanity stood at the threshold of its greatest achievement. The first interstellar journey was no longer just a dream, but a reality. The crew aboard Starbound 3 had navigated a treacherous journey, survived a life-threatening crisis, and, against all odds, pushed forward with unwavering resolve. Now, as the spacecraft finally neared the Alpha Centauri system, the culmination of humanity's aspirations to reach the stars was within grasp. The journey, which had taken over a decade, had been filled with moments of triumph and terror, each one a testament to the strength of the crew and the technology that had made it possible. But as the spacecraft's warp drive thrusters kicked in once more, the final push for Alpha Centauri was underway. The crew felt the acceleration as the Alcubierre drive brought them closer to their destination, closer to a world no human had ever seen. Captain Marcus Hughes stood in the command center, staring out into the vastness of space. His mind raced, thinking back to the many milestones that had brought them to this moment. There had been so many uncertainties, so many points along the way where they could have turned back, where failure could have ended the mission. Yet here they were, only months away from reaching Alpha Centauri, humanity's first star system beyond the sun. Despite the achievements, there was a palpable sense of tension. Even after all the successful tests and near-successful missions, this final stretch of the journey was unlike any other. The unknowns were still many. The systems were being pushed to their limits. The crew, weary after a decade of isolation, knew that the next few months would be the most critical of their lives. As the spacecraft moved deeper into the Alpha Centauri system, Captain Hughes addressed the crew. "This is it," he said, his voice steady, though the weight of the moment was evident. "We're about to make history. What we're doing here is not just for us. It's for everyone back home, for the future of humanity. Whatever happens next, we're ready." Dr. Naomi Patel, the mission's biologist, and the rest of the crew, including Dr. Elena Ramirez, Zhu Wei, and Samuel Nguyen, gathered in the observation bay. The Starbound 3 had entered the gravitational pull of Alpha Centauri's star, and through the massive observation windows, they could see the light from the distant stars reflected in the spacecraft systems. In the final approach to the Alpha Centauri A, the crew was tasked with conducting a series of planetary scans to identify habitable planets within the system. While Alpha Centauri A itself was a stable, sun-like star, the real goal was to locate potential planets that could support life, worlds that could one day become the new home for humanity. The science team worked tirelessly, mapping the planets in the system, using the advanced sensors to scan for signs of water, atmosphere, and life. But as the scans of the planets began to come in, something unexpected happened. Alpha Centauri b, the secondary star in the system, had a much stronger gravitational influence than anticipated, causing disruptions in the spacecraft's trajectory. The data suggested that the system was much more dynamic than the initial models had shown. As the spacecraft approached one of the closest exoplanets, Alpha Centauri b flat, a massive gravitational anomaly caused a temporary system malfunction. For the crew, it was a moment of uncertainty. The spacecraft's course had shifted unexpectedly, and for a moment, the mission appeared to be in jeopardy. The systems that had been so meticulously designed to withstand the pressures of deep space were being tested like never before. In that moment of crisis, the entire crew was reminded of how fragile the journey really was. Captain Hughes and Zhao Wei, the lead engineer, worked together to recalibrate the spacecraft's systems. With each passing minute, they grew more confident in their ability to correct the spacecraft's course. Dr. Ramirez and Dr. Patel ran simultaneous simulations to assess the impact of the anomaly on their life support systems. In the midst of this, Samuel Nguyen, who had developed the AI system, ran a series of diagnostic commands to recalibrate the spacecraft's systems to account for the shifts in the gravitational forces at play. As the tension built and the crew worked against the clock, it became clear that they were on the verge of making history. The AI system, with its real-time data analysis, enabled the crew to recover the spacecraft's trajectory, and within hours the ship was back on course. They had successfully navigated one of the most difficult anomalies in space travel, demonstrating their adaptability, teamwork, and ability to think critically under pressure. The recovery, however, wasn't just a technical achievement. It was symbolic of the journey itself. The crew had faced crisis after crisis, yet they had not given up. They had weathered the emotional, physical, and technological storms, each challenge bringing them closer to their goal. The success of the recovery brought a renewed sense of hope and excitement, not just for the crew, but for humanity as a whole. This was a mission that would be remembered for centuries to come. A mission that proved that, no matter the odds, humanity could achieve the seemingly impossible. As the Starbound 3 finally entered orbit around Alpha Centauri b flat, the crew prepared for the first interstellar landing. The planet, though far from Earth's ideal conditions, was the first potential world that could be explored for future colonization. The significance of the mission was not lost on the crew. They were standing on the brink of a new era in human history, the first step toward humanity's expansion into the stars. The historic moment arrived as Captain Hughes, Dr. Ramirez, and Dr. Patel made their descent to the planet's surface in the lander module. As the lander touched down on the alien terrain, the first human footprints on an exoplanet were imprinted into the surface. This moment, captured in photographs and data, was the culmination of everything the mission had worked for. It was not just the first landing on a distant world. It was the beginning of the next chapter for humanity, a new era of exploration and discovery that would continue for generations. As the crew of Starbound 3 disembarked and planted the flag of humanity on the surface of an alien world, the impact of their success rippled throughout the Earth. The moment was broadcast to billions of people across the planet, who watched in awe as their species achieved what had once been thought impossible. The world united in celebration of this achievement, a monumental event that brought the planet together, reminding everyone of the infinite possibilities that lay ahead. In the coming years, the Alpha Centauri system would be the focus of intense scientific exploration, with teams working to understand the planet's potential for human habitation. The successful interstellar journey had paved the way for future missions to distant star systems, and humanity's quest to become a multi-planetary species had officially begun. The achievement of mission Starbound 3 was more than just a technical victory. It was a triumph of human ambition, unity, and the belief that, no matter the challenges, humanity could reach for the stars and beyond. The success of mission Starbound 3, the first interstellar mission to reach another star system, marked the dawn of a new era for humanity. The immediate aftermath of the mission was filled with celebration, reflection, and an overwhelming sense of accomplishment. Yet the true significance of the achievement went beyond the historic landing on Alpha Centauri b. The legacy of mission Starbound 3 would shape the future of space exploration, scientific discovery, and humanity's place in the cosmos for centuries to come. Upon the crew's return to Earth, the world greeted them as heroes. The journey had been long, fraught with uncertainty and at times perilous. Yet the astronauts, led by Captain Marcus Hughes, Dr. Naomi Patel, Dr. Elena Ramirez, Zhao Wei, and Samuel Nguyen, had successfully completed the first interstellar journey in history. The crew's efforts were celebrated globally, with world leaders and citizens alike honoring their bravery, determination, and unwavering commitment to the mission. They were not only symbols of human achievement, but also the catalysts for a new era of exploration that transcended national boundaries. As the crew members returned to Earth, they were met with a hero's welcome, but the true impact of their success extended far beyond the celebrations. The mission's success raised important questions about the future of space exploration. What lay ahead for humanity? Would the stars truly become a new home for the human race? The answers to these questions would not come immediately, but they would slowly unfold over the coming decades. The scientific legacy of Mission Starbound 3 was vast. The data collected during the mission, including planetary scans, radiation readings, and atmospheric analysis, reshaped humanity's understanding of exoplanets. The discovery of Alpha Centauri B-flat, and the data gathered from it, provided the first real clues as to the nature of planets beyond our solar system. It opened the door to the study of planets in distant star systems, many of which might one day be capable of supporting life. The mission also had a profound impact on astronomical research. For the first time, scientists had data from an interstellar, allowing them to refine their models of how planets form, how stars interact with their planetary systems, and how life might be sustained on distant worlds. The findings from Alpha Centauri B-flat, though not immediately promising in terms of habitability, provided key insights into the types of conditions that could support life, as well as the challenges humanity might face in future colonization efforts. Technological breakthroughs that had been developed for the mission now found applications in other fields. The fusion energy systems that powered the spacecraft's propulsion and life support systems, for example, would be adapted for use on Earth, helping to address the growing demand for clean, sustainable energy. Similarly, advancements in space-time manipulation, as part of the Alcubierre drive's development, would spark innovations in transportation and communication systems, potentially revolutionizing industries on Earth. The AI systems developed to manage the spacecraft systems and assist the crew also had broader implications. These systems would form the foundation for autonomous vehicles, smart cities, and advanced robotics, marking the beginning of a new era in AI-driven technologies. While the scientific and technological impacts of the mission were profound, the social and psychological effects were equally significant. The success of Mission Starbound 3 united humanity in a way that few events had ever done before. For the first time in history, people from all corners of the Earth shared in the excitement of a common achievement. The mission transcended borders, languages, and ideologies, fostering a sense of global unity and cooperation. In many ways, the mission became a symbol of humanity's potential when it worked together toward a common goal. It showed that, despite the challenges facing Earth climate change, political division, economic inequality, the pursuit of something greater, the exploration of the unknown, could bring people together and offer hope for the future. As the global community celebrated the mission's success, people began to look to the stars not as distant, unreachable points in the sky, but as destinations for the human race. The psychological impact of the mission was also significant. The crew of Mission Starbound 3 had faced isolation, adversity, and immense pressure throughout their journey. Their return to Earth was not just a homecoming, but a celebration of the human spirit. The ability to endure, adapt, and thrive in the face of overwhelming odds. The success of the mission proved that humanity was capable of overcoming its limitations, both technological and psychological, and that the human race could reach beyond its home planet to explore new worlds. In the years following the mission, the success of Mission Starbound 3 continued to inspire people around the world. Young students chose careers in science, engineering, and space exploration, inspired by the crew's example. The idea of interstellar exploration became a central focus of the next generation's ambitions. People began to believe that the stars were within humanity's reach, and that the future was one of exploration and discovery. In the long term, Mission Starbound 3 had a transformative impact on human civilization. The success of the mission marked the beginning of a new era in which humanity was no longer limited to its home planet. The technology developed during the mission paved the way for future interstellar voyages, with the next goal being the potential colonization of other star systems. The first major mission to Alpha Centauri had proven that interstellar travel was possible, but it was just the beginning. Colonization efforts would follow, with the goal of establishing permanent human settlements on distant planets. These efforts would take time, but the success of Mission Starbound 3 demonstrated that humanity could make the leap from Earth to the stars, marking the beginning of humanity's multiplanetary future. The mission also had a profound effect on how humanity viewed its place in the universe. It fostered a sense of cosmic humility, as people realized that they were not alone in the vast expanse of space. It sparked a renewed interest in the search for extraterrestrial life, and the possibility that other intelligent species might exist in the universe. In the decades following the mission, space exploration became a central part of global priorities. Governments, private companies, and international organizations continued to work together to expand humanity's presence in space. Mars became the next target for colonization, and new missions were launched to explore distant planets, moons, and asteroids. The legacy of Mission Starbound 3 lived on as humanity reached further into the cosmos. As the years passed, the key figures of Mission Starbound 3 reflected on the impact of their journey. Captain Marcus Hughes, who had led the crew through the crises of the mission and emerged as a symbol of leadership, spoke of the transformative power of space exploration. "We didn't just reach Alpha Centauri," he said in a public address years later. "We reached the future. We reached the stars, not just for ourselves, but for all of humanity." Dr. Elena Ramirez, whose scientific work had made interstellar travel a reality, looked back on the mission with pride. "When we started, it was all theory, all speculation, but now we know it's possible. We've made history, and this is only the beginning." The mission's legacy, however, wasn't confined to the individuals who made it happen. It became a part of the collective human experience. Mission Starbound 3 reminded humanity that there are no limits to what can be achieved when people unite in pursuit of a common goal. The mission was not just a leap into the stars, it was a leap into humanity's future. The success of Mission Starbound 3 and the achievement of humanity's first interstellar journey offered a rich narrative filled with profound lessons and universal themes. These lessons were not confined to the realms of space exploration, technology, or scientific discovery. They transcended these fields and spoke to humanity's deepest impulses: the desire to explore, to understand, and to push beyond the boundaries of the known. As humanity ventured farther into the stars, the broader themes and lessons of the mission became integral to understanding not only the technical achievements, but also the cultural, ethical, and philosophical shifts that came with interstellar exploration. At the heart of Mission Starbound 3 was humanity's unquenchable curiosity, the innate desire to explore the unknown. This desire had driven human civilization from its earliest days, from the first ocean voyages to the exploration of the Earth's deepest caves and highest mountains. The journey to the stars was simply the next step in this age-old quest. Humanity had long looked to the heavens, wondering what lay beyond the reach of their telescopes. But now, that wonderment was being transformed into reality. The lesson here is that exploration is not just about reaching new frontiers, but about understanding the very essence of what it means to be human. It is the pursuit of knowledge, the desire to learn about our universe and our place within it. As the crew aboard Starbound 3 gazed out into the vast expanse of space, they did so with the knowledge that they were not just exploring other planets or star systems. They were expanding the scope of human understanding. This sense of exploration transcended the individual mission and became a reflection of humanity's core drive. The pursuit of exploration, as demonstrated by Mission Starbound 3, is something that has driven humanity to overcome unimaginable obstacles and achieve what was once considered impossible. It is a reminder that our desire to explore, to understand, and to reach for something greater will continue to fuel progress and innovation. Whether on Earth or in space, humanity's pursuit of the unknown is what continues to push the boundaries of possibility. The achievement of interstellar travel was not the result of a single nation or organization. It was the product of global cooperation, a collective effort that united countries, private companies, and international organizations to work toward a common goal. This collaboration was unprecedented in human history, a demonstration of what humanity can accomplish when it sets aside differences and focuses on a shared vision. Throughout the Mission Starbound 3 program, nations from all corners of the world came together to pool resources, expertise, and technology. Governments, scientific institutions, and private sector companies worked hand in hand to overcome the immense challenges of interstellar travel. It was a model for international cooperation, one in which the benefits of the mission would not just be for one nation or group, but for all of them, humanity. The lesson learned here is that unity and collaboration are essential when facing monumental challenges. While political divisions and differences will always exist, the pursuit of a common goal, especially one with the potential to benefit all of humanity, can transcend these divisions. The mission showed that by cooperating, sharing knowledge, and aligning efforts, humanity could achieve feats that would have been unimaginable alone. This lesson is crucial as humanity faces future global challenges, from climate change to technological inequality. The success of Mission Starbound 3 provides a compelling example of the potential for global cooperation in addressing issues that affect all of humanity, proving that when people unite in purpose, they can overcome even the most complex and daunting obstacles. Mission Starbound 3 was not without its crises. The unexpected life support system failure, the navigational anomaly in the Alpha Centauri system, and the subsequent systems malfunction tested the crew's resilience. Despite the high stakes and life-threatening situations, the crew's ability to adapt and respond to crises proved to be one of the most valuable lessons of the mission. The crew of Starbound 3, especially during the life support system malfunction, was forced to work under immense pressure. It wasn't just their technical skills that ensured their survival. It was their resilience in the face of danger, their ability to keep calm under pressure, and their unwavering commitment to solving problems. The mission showed that failure was not the end. It was a step in the process of success. Each obstacle became an opportunity to innovate, adapt, and grow. The lesson here is that resilience and adaptability are vital traits for overcoming adversity. Humanity continues to face challenges in space exploration, climate change, and other global crises. The ability to adapt quickly, learn from mistakes, and persevere through adversity will be essential. Mission Starbound 3 proved that resilience is not just about enduring hardship. It's about using that hardship as a catalyst for progress and innovation. As humanity extends its reach into space, ethical considerations regarding exploration and colonization will become increasingly important. The success of Mission Starbound 3 raised several key ethical questions. How should humanity interact with potentially habitable planets? What responsibilities do we have to preserve these environments? Should we colonize planets? Or should we prioritize scientific exploration first? These ethical questions became particularly important as the crew of Mission Starbound 3 reached Alpha Centauri B flat, where the first data indicated that the planet could potentially support life. While the planet was far from Earth-like, it raised the question of whether humanity had the right to explore or even settle on a planet that could potentially harbor its own form of life. The ethical considerations surrounding space colonization, resource extraction, environmental impact, and the rights of any potential indigenous life are issues that humanity will have to grapple with as it moves into the next phase of space exploration. The lesson here is that space exploration is not just about technological advancement or scientific discovery. It is also about understanding the responsibility that comes with exploration. As humanity extends its reach into the stars, it must ensure that its actions are guided by ethical principles that respect the environments and potential life forms it encounters. The future of space exploration will require a careful balance between exploration and preservation, scientific discovery, and ethical responsibility. At its core, Mission Starbound 3 was a triumph of the human spirit. It represented the endless desire to push beyond the boundaries of the known world, to venture into the stars and explore the unknown. The mission exemplified the courage and curiosity that define humanity's greatest achievements. The journey to the stars was not just a technical achievement, it was a manifestation of hope, a reminder that humanity's capacity to dream and to strive for greatness is limitless. As Captain Hughes and his crew embarked on their historic mission, they carried with them the hopes and dreams of every person on Earth. The success of Mission Starbound 3 showed that, when humanity dares to dream and pursues those dreams with courage and determination, there are no limits to what it can achieve. The lessons of Mission Starbound 3 are timeless: the power of curiosity and exploration, the strength of unity, the resilience to face adversity, the responsibility to act ethically, and the importance of dreaming beyond Earth. These are lessons that will continue to guide humanity as it takes its next steps into the cosmos. The achievement of Mission Starbound 3, humanity's first interstellar journey to another star system, is a defining moment in history, one that signifies the beginning of a new chapter in the story of human exploration and discovery. The success of the mission not only accomplished what had long been thought impossible, but also set the stage for a future where the stars are no longer distant, unreachable points in the sky, but destinations within humanity's grasp. As Captain Marcus Hughes and the crew of Starbound 3 set foot on the surface of Alpha Centauri B flat, the reality of interstellar travel became undeniable. Their journey marked the end of one era and the beginning of another. The mission had not just proven that interstellar travel was possible, but it had shown that humanity had the determination, the creativity, and the resilience to achieve it. The world watched as a new chapter of space exploration was written, and the implications for humanity's future are profound. The immediate aftermath of the mission was filled with celebration and reflection. The data collected from the Alpha Centauri system, the first exoplanetary scans, and the insights into long-term space travel would shape future missions. Yet, while the success of Mission Starbound 3 was momentous, it was only the beginning of a long journey ahead, one that would take humanity far beyond Alpha Centauri, to new star systems and planets, perhaps even to distant galaxies. In the years following the mission, the most immediate goal would be colonization. The next steps would involve expanding humanity's presence in space, starting with the colonization of nearby exoplanets that were found to be suitable for human habitation. The technological advances achieved during the mission, particularly in propulsion and life support systems, would be applied to the establishment of permanent colonies on these new worlds. As humanity moved beyond Earth, it would not just be about survival, but about creating thriving, sustainable societies on distant planets. Mars would continue to be the focal point for colonization efforts in the solar system. While Mission Starbound 3 opened the door to interstellar exploration, Mars would remain a crucial stepping stone for humanity, providing a platform to test the technologies and strategies necessary for interstellar expansion. In the coming decades, space agencies and private companies would begin to work together on large-scale terraforming projects on Mars, as well as the development of new space habitats that could support human life on distant planets and moons. However, the dream of reaching the stars would not stop at Alpha Centauri. Mission Starbound 4, launched in the early 2060s, would set its sights on a new goal: the Beta Centauri system, which was believed to have planets in the habitable zone capable of supporting life. As the pace of space exploration accelerated, the dream of interstellar travel would continue to fuel scientific discovery and technological advancement. Each mission would push the boundaries of what was possible, leading humanity to new frontiers. Technological advancements made during Mission Starbound 3 would have profound effects beyond space exploration. The fusion reactors, space-time manipulation technologies, and AI systems developed for the mission were not confined to interstellar travel. These technologies would be adapted and deployed on Earth, transforming industries, reshaping the energy sector, and advancing the way humanity lived on its home planet. The long-term impact on energy generation, transportation, and resource management would be felt globally, leading to cleaner, more sustainable practices that could help address some of Earth's most pressing problems. As humanity moved toward the stars, however, ethical considerations would continue to evolve. The question of how to treat planets, moons, and other celestial bodies would be a defining issue for future generations. The possibility of encountering extraterrestrial life, whether microbial or intelligent, would demand careful ethical consideration, not only in how humanity explored new worlds, but in how it interacted with them. The International Space Exploration Coalition, ISCC, would need to create and enforce guidelines for planetary protection, ensuring that humanity's expansion into space was done responsibly, respecting the natural environment and any life forms it might encounter. Alongside the ethical questions, the psychological and sociological effects of long-term space travel would also need to be addressed. As humanity established permanent colonies on distant planets, the effects of isolation, time dilation, and intergenerational travel would require careful consideration. What would it mean to grow up on a colony light years from Earth? How would families and communities adapt to the challenges of life in space? These questions would form the basis of new disciplines in space psychology and sociology, as experts worked to ensure the long-term sustainability of human settlements beyond Earth. Yet, as profound as these practical challenges are, the human spirit would remain at the heart of this new age of exploration. Just as the ancient explorers set out across oceans in search of new worlds, so too would humanity reach for the stars, driven by a shared vision of discovery, growth, and the possibility of life beyond Earth. The first steps on Alpha Centauri B-flat would serve as a symbol of humanity's unyielding desire to explore, to expand, and to evolve. The future prospects of mission Starbound 3 lie not only in the technologies and missions it inspired, but also in the broader impact on humanity's worldview. The realization that the stars were no longer out of reach would inspire countless future generations to pursue careers in science, engineering, and space exploration. The notion that humankind is capable of achieving the unimaginable would resonate through the years, spurring the pursuit of even bolder goals. Whether it was a journey to the outer planets, the colonization of moons and exoplanets, or the search for intelligent extraterrestrial life, the legacy of mission Starbound 3 would remain a powerful force driving humanity forward. As the mission set its sights on new star systems, humanity would face new challenges, but the lessons learned from Starbound 3 resilience, unity, ethical responsibility, and the spirit of exploration would continue to guide future endeavors. Humanity's presence in the stars would no longer be a question of if, but when. And as each new leap was taken, the ultimate goal of spreading the light of human civilization to the furthest reaches of space would draw nearer. In the end, the story of mission Starbound 3 is a story of humanity's dreams and potential. It is a testament to the power of vision and determination, to the relentless pursuit of knowledge, and to the belief that the future lies not on Earth alone, but among the stars.